It all started with a bold launch as a fragile spacecraft made with great care set off on a journey that no one had ever even thought of trying. Voyager-Two wasn't just another spacecraft, it was humanity's first messenger to the outer planets, quietly watching and exploring the farthest parts of our solar system. Its mission was to find the secrets of faraway worlds, so strange and unknown that we could barely understand their existence. As Voyager-Two traveled through space, it passed by huge gas giants and icy moons, showing environments unlike anything we had ever imagined. The information it sent back to Earth changed our understanding of these distant planets forever. It showed us Jupiter's violent storms, Saturn's beautiful rings, and Neptune's strong winds that moved faster than sound. But it was Voyager's short encounter with Uranus, the most mysterious and least studied of the gas giants, that left us with some of the most puzzling secrets. Hidden within the planet's magnetic field, its moons, and its strange tilt, Uranus gave us mysteries that still confuse scientists today. Even though Voyager-Two's mission ended many years ago, its discoveries still live on in the questions we try to answer. And now, using new technology and fresh ideas, we're learning even more about these faraway worlds, especially Uranus, uncovering secrets that Voyager itself could never have imagined. In 1986, NASA's Voyager-Two spacecraft made an incredible flyby of Uranus, marking a major milestone in our exploration of the outer solar system. For the first time, scientists had the chance to closely study this distant and mysterious planet. Uranus, with its striking blue-green color, faint rings, and unusual tilt, rotates in a way unlike any other planet. It spins on its side, like a rolling ball. But beneath the beautiful images and data gathered during this historic encounter, some findings suggest our understanding of Uranus, especially its magnetosphere, might need to be updated. Voyager-Two's journey to Uranus happened under unusual circumstances. Just days before its arrival, a rare and powerful burst of solar wind, an intense stream of charged particles from the Sun, struck the planet. This surge of solar wind was so strong that it compressed Uranus's magnetic field to just a fraction of its usual size. Normally, solar wind constantly flows from the Sun, shaping the magnetic environments of planets and creating protective shields called magnetospheres that guard them from harmful solar radiation. However, this particular solar wind burst was so intense that it shrank Uranus's magnetosphere to only about 20% of its normal volume, which affected the data Voyager-Two was able to collect. A recent study published in Nature Astronomy suggests that such extreme solar wind events are rare, happening only around 4% of the time. Had Voyager-Two arrived just a week earlier, it would have encountered a much larger magnetosphere, more similar to those of other giant planets like Jupiter, Saturn, and Neptune. This means that the data Voyager collected might not fully represent what Uranus's magnetosphere typically looks like. For a long time, scientists thought that Uranus's magnetosphere, the region influenced by its magnetic field, was unusually weak. They believed it had low levels of plasma, a type of matter where atoms break into charged particles, and intense radiation belts. Plasma is a common feature in the magnetospheres of other planets, especially those with strong magnetic fields. Data from the Voyager spacecraft suggested that Uranus's magnetosphere lacked plasma from both the solar wind and its moons, making it seem unusually empty. However, new research has changed that view. Scientists now believe that the solar wind, which is a stream of charged particles coming from the Sun, may have been preventing plasma from building up in the planet's magnetosphere. This new understanding corrects the earlier idea that Uranus was almost entirely devoid of plasma. By re-examining the Voyager data with this new information about the solar wind's strength, researchers now think that Uranus's magnetosphere is more similar to the magnetospheres of other giant planets than previously believed. This shift in understanding has also led to new insights about Uranus's moons, Titania and Oberon. Earlier observations from Voyager suggested that these moons orbit outside Uranus's magnetosphere, but new research indicates that they might be inside its protective magnetic bubble. This discovery is important because it could affect our understanding of these moons, particularly the potential for subsurface oceans beneath their icy surfaces. Scientists are increasingly interested in this possibility, as it could open up new avenues for exploring life beyond Earth, particularly in the outer reaches of our solar system. Now, let's take a closer look at what we understand about solar wind. When charged particles from the Sun meet a planet's magnetic field, they apply pressure that can compress, stretch, or even change the shape of the planet's magnetosphere. This interaction is never the same. It changes all the time due to factors like solar activity and how far the planet is from the Sun. Planets with strong magnetic fields, like Earth, Jupiter, and Saturn, are especially affected by the solar wind. This wind can create protective shields that help keep harmful radiation from reaching the planet's surface. In this way, the magnetosphere acts like a defense system, protecting the planet from dangerous particles. It's shaped by the planet's magnetic field, deflecting and redirecting these charged particles away. However, the magnetosphere isn't invincible. Its size and strength depend on the pressure of the solar wind, which changes constantly in both strength and speed. For example, when Voyager-Two passed by Uranus in 1986, the conditions were extreme. The solar wind's dynamic pressure was at its highest, and this pressure is a result of both the speed and density of the solar wind. Under normal conditions, Uranus's magnetosphere extends about 22 to 25 times the radius of the planet. But during the Voyager flyby, the boundary between the planet's magnetic pressure and the solar wind's pressure, called the magnetopause, was pushed inward to just 17.3 radii. As the solar wind's pressure grew stronger in the days before the flyby, the size of the magnetosphere shrank significantly. This compression of the magnetosphere not only affected its outer boundary, but also likely influenced the planet's radiation belts. Normally, radiation belts around planets are formed by plasma from the planet's atmosphere, moons, and solar wind. However, the powerful solar wind during Voyager's approach likely pushed plasma out of Uranus's magnetosphere, leaving a gap and changing the typical behavior of its radiation belts. This led to an unexpected and intense belt of electron radiation that puzzled scientists for years, until new research finally provided answers. When Voyager-Two flew by Uranus, it revealed some surprising features of the planet that have left scientists scratching their heads. The spacecraft's data showed that Uranus has a magnetic field that is not only tilted unusually, but also offset, making its magnetosphere appear very extreme compared to other planets in our solar system. This discovery led many to believe that Uranus's magnetic environment was unique. However, more recent research suggests that this interpretation might not fully explain the planet's behavior. Scientists now understand that changes in the magnetosphere, like those seen at Uranus, are not permanent or static. Instead, they trigger a chain of complex processes. For example, when the pressure from solar winds increases, it pushes hot plasma from Uranus's magnetotail into the planet's inner magnetosphere. This process is similar to what happens on other planets, like Saturn. When the solar wind compresses the planet's magnetic field, it can boost the intensity of certain types of radiation and cause shifts in the magnetic field. For Uranus, these solar wind events led to stronger electron radiation belts and altered the makeup of the plasma in its magnetosphere. Interestingly, this means that under certain conditions, Uranus's magnetosphere behaves much more like those of other giant planets, such as Jupiter and Saturn. This new understanding helps scientists make better sense of how Uranus's magnetic environment works and how it compares to other planets in our solar system. When the magnetosphere of a planet gets compressed, it can cause the radiation belts to become more charged, much like what happens during geomagnetic storms on Earth. This effect is well understood on Saturn, where the compression of its magnetosphere leads to an increase in electron radiation. On Uranus, something similar could have occurred, boosting the electron activity in the radiation belts, even though the planet was previously thought to have very little plasma in its environment. This sudden surge in radiation during the compression could have also sparked changes in the planet's magnetotail dynamics, including a process called magnetic reconnection. Magnetic reconnection, which has been observed on planets like Earth and Saturn, could have caused plasma to be expelled from the magnetotail and pushed into the inner magnetosphere. This would have altered the plasma density and radiation levels. On Saturn, events like this have been linked to stronger radiation belts and more intense auroras. However, the behavior of Uranus's magnetosphere during such extreme solar wind events is harder to predict. While we have gathered a lot of information about how magnetospheres react to compression on other planets, Uranus's unique features, like its extreme tilt and oddly shaped magnetic field, make these interactions more complex. The tilt of Uranus could create special magnetospheric patterns that are different from those on other planets, possibly explaining why the electron flux was stronger and why its radiation belts behaved unusually. Scientists have recently revisited the behavior of Uranus's magnetosphere, which is the region around the planet influenced by its magnetic field. This new understanding is important because it helps researchers assess how these conditions might impact the potential for subsurface oceans on Uranus's moons. The outer moons, Titania and Oberon, have long fascinated scientists, particularly when it comes to whether they might have hidden oceans beneath their icy surfaces. These moons orbit Uranus at distances of 17 and 22.8 times the planet's radius, putting them in a special position relative to Uranus's magnetic field. Moons that are located closer to Uranus, like Miranda, Ariel, and Umbriel, are more likely to have subsurface oceans that can be detected using magnetic induction. This is because Uranus's magnetic field would create electrical currents in the moon's conductive layers, which would produce measurable signals. However, Titania and Oberon are a bit more complicated. They orbit near or just outside the magnetopause, which is the boundary between Uranus's magnetic influence and the solar wind that flows through space. Because of this, these moons are less likely to feel the strong effects of Uranus's magnetic field. Earlier studies suggested that Titania and Oberon might even be outside the planet's magnetosphere for large parts of their orbits, which would make detecting subsurface oceans difficult. The moons would be exposed to the solar wind and a turbulent region called the magnetosheath, making it nearly impossible to measure magnetic signals that could reveal the presence of hidden oceans. However, new data has brought a surprising twist. It seems that Titania and Oberon likely remain within the magnetosphere for most of their orbits, which means that the possibility of detecting subsurface oceans on these moons is more feasible than previously thought. This discovery could open up exciting new avenues for future research into the mysteries of Uranus and its moons. Simulations show that Titania has less than a 4% chance of crossing Uranus's magnetopause, while Oberon has a slightly higher probability of about 13%. This suggests that, unlike what we once believed, both moons are generally within the protective magnetic shield of Uranus. This discovery is important because it changes how we approach the idea of subsurface oceans on these moons. Since they are mostly shielded by Uranus's magnetosphere during their orbits, the possibility of magnetic induction becomes more likely, making it easier to explore the potential for hidden oceans beneath their surfaces. This finding also has big implications for how the moons interact with the planet's magnetosphere. Normally, the magnetosheath is filled with plasma from the solar wind, but because Titania and Oberon orbit inside Uranus's magnetosphere, they mostly interact with the planet's plasma. This means the interactions are less likely to interfere with measurements of magnetic induction, improving the chances of detecting subsurface oceans. Science is always evolving, constantly refining what we know and sometimes overturning previous assumptions. The case of Uranus shows how new data can challenge old beliefs and push us to rethink what we thought was true. To fully understand this distant planet, we need to revisit it with advanced technology. A future orbital mission could provide continuous, high-resolution data, allowing us to study Uranus, its moons, and its rings in much greater detail than ever before. As plans for future missions to the Uranus system move forward, gaining a better understanding of the positions of Titania and Oberon within the planet's magnetic field is crucial. In addition, knowing how the solar wind interacts with the magnetosphere will play a key role in determining flight paths. This will ensure that spacecraft reach these moons at the best possible times for gathering important data. Magnetic studies, which have already proven effective on other icy moons like Europa and Enceladus, can now be applied to Titania and Oberon with more certainty. A mission focused on these moons could use magnetic sensors to explore their internal structures, looking for signs of liquid water beneath their icy surfaces. This mission could also help fill in the gaps in our knowledge, deepening our understanding of distant worlds in the outer solar system. The future of exploration in this far-off region is taking shape, with both established space agencies and rising powers prioritizing missions to Uranus and its moons. In 2022, NASA included an orbital mission and probe to Uranus on its priority list for the 2023 to 2033 Planetary Science Survey. This move highlights the growing importance of studying ice giants, which have remained largely unexplored. NASA's proposed mission, known as the PUS, Plasma, Environment, Radiation, Structure, and Evolution of the Uranian System, is set to launch in February 2031, with an expected arrival at Uranus in 2043. The spacecraft will focus on studying the planet's plasma, magnetic fields, and overall heliophysical environment, offering valuable insights into the processes that govern ice giants. This mission will be a turning point in Uranus research, and the spacecraft will also gather data on the planet's atmosphere and rings. The launch window for this mission is between 2030 to 2034. China is also entering the field with its Tianfu mission, set to launch in 2030 to 2034. This mission, which will be carried by a Long March 5 rocket, will send 2 spacecraft on separate journeys. One will explore Jupiter's moon Callisto, while the other will fly by Uranus. This marks China's first mission to study the ice giants, and even though the spacecraft will be smaller than NASA's, it will still be equipped with instruments to study Uranus's magnetosphere. The mission will rely on a series of flybys to gain the necessary momentum for its journey into the outer solar system. The Voyager missions were instrumental in exploring the outer planets, setting the stage for future discoveries. However, our true understanding of space is driven by an endless curiosity and the spirit of exploration. As we continue to look to the stars, the legacy of past missions pushes us forward, providing a solid foundation for humanity to expand its knowledge of the universe. Far out in the endless stretch of space, amid countless stars and galaxies, there exists a faint whisper, a whisper from a star that has journeyed across light years to reach us here on Earth. This isn't a tale from a science fiction novel, but a real discovery in the universe, a glimpse into the ever-expanding knowledge we're gaining about the cosmos. Scientists, listening closely to the vastness of space, have picked up an intriguing signal, a radio wave coming from a star system not so different from our own. This star, called YZ Ceti, is located just 12 light-years away. But this is no ordinary signal, it holds a clue. It's carrying a potential signature of a magnetic field similar to the one that protects our planet. Let's embark on a journey light years away to uncover the mysteries of these radio signals from deep space and explore the magnetic fields of distant worlds. In the vast, quiet expanse of the universe, these radio signals are like whispers that travel across unimaginable distances. But what are these signals? And how do they manage to cross such enormous stretches of space? The answers lie in the strange and fascinating phenomena of space itself. Radio signals are a type of electromagnetic wave, much like light, X-rays, or microwaves. These signals come from a wide range of sources, including distant stars, galaxies, and even human-made satellites and spacecraft. They travel at the speed of light, carrying valuable information across enormous stretches of space. These signals help us learn about the makeup of stars and the existence of planets, and even give us clues about the origins of the universe itself. But how do we pick up these distant signals? The key is a technology called radio astronomy. Radio telescopes, like the Very Large Array in New Mexico or the now inactive Arecibo Observatory in Puerto Rico, are built to capture and study radio signals from space. These massive instruments act like our cosmic ears, listening for the faintest sounds from the farthest reaches of the universe. Once a radio signal is captured by one of these observatories, it is carefully examined using advanced computer models and algorithms. This analysis can reveal a wealth of information about the signal's origin, such as where it's coming from, how far away it is, and even details about its physical nature. But radio signals from space aren't just important for science. They have real-world uses as well. For instance, signals from satellites help with GPS navigation, weather predictions, and monitoring the Earth. These signals are an essential part of the modern technological world we rely on every day. The constellation of Cetus, known as the Sea Monster, holds within it a star that sends whispers to us across the vastness of space. This star is named WISE YZ Ceti. It's a red dwarf, much smaller and cooler than our own Sun, and is located just 12 light-years away, quite close in cosmic terms. But what truly makes WISE YZ Ceti fascinating isn't the star itself, but what orbits it. At least 3 exoplanets are known to revolve around this star, and one in particular, YZ Ceti b, stands out. YZ Ceti b is a rocky, Earth-sized planet that orbits extremely close to its star. It's so close that it completes a full orbit around WISE YZ Ceti in just 1.6 Earth days. Recently, scientists at Bucknell University, led by Professor Jackie Villadsen and her colleague J. Sebastian Panetta, made a surprising discovery. Using the Very Large Array, they detected a repeating radio signal coming from YZ Ceti. The signal, recorded at a frequency of 2 to 4 GHz, seems to change in rhythm with both the star's rotation and the orbit of YZ Ceti b. This suggests an interaction between the planet's magnetic field and the star itself. While YZ Ceti b is unlikely to host life due to its extreme proximity to its star, this discovery is still incredibly important. It shows that we can detect the magnetic fields of exoplanets, offering a new way to study distant worlds and even search for planets that might be more suitable for life. Magnetic fields are crucial in protecting planets from harmful radiation and play a key role in the planet's overall habitability. This breakthrough could change how we find life-friendly planets in the future. But what does this mysterious signal truly mean? And why are magnetic fields so essential in our search for life? To understand these questions, we need to explore the invisible forces that shape the universe around us. Magnetic fields are one of the most important forces in nature. They guide the needle of a compass, helping us find our way, and play a crucial role in the lives of many animals, like birds, by helping them navigate during their long migrations. They also act as a shield, protecting our planet from the harmful solar wind that constantly blows from the sun. But magnetic fields aren't just something we experience here on Earth. They have a big influence beyond our planet, too. For instance, the sun has a powerful and ever-changing magnetic field that controls much of its behavior. From the formation of sunspots to the sudden bursts of energy known as solar flares, the sun's magnetic field is behind it all. Magnetic fields also shape galaxies, guiding the movement of gases between stars and influencing the birth of new stars. Perhaps one of the most fascinating aspects of magnetic fields is their potential to help planets support life. A strong magnetic field can protect a planet from the dangerous radiation emitted by its star. This protection helps preserve a planet's atmosphere, which is essential for maintaining conditions that might support life. This is why finding a magnetic field on a distant planet like exoplanet YZ Ceti b is so exciting. It could tell us a lot about the planet's atmosphere and its ability to support life. To fully understand how magnetic fields impact the search for life beyond Earth, we need to explore how they influence the signals we receive from space, especially radio waves. By studying the relationship between magnetic fields and these signals, we can learn more about distant planets and their potential to harbor life. Radio signals are a form of energy that travels through space as waves, made up of electric and magnetic fields that constantly move and change direction. These fields don't just move on their own, they can interact with other magnetic fields they encounter along the way. When a radio signal passes through a magnetic field, it can undergo several changes. For instance, its path might bend, a phenomenon called deflection. The alignment of its electric field, known as polarization, can also twist. Even the frequency, the number of waves passing a point in a specific amount of time, can shift. These changes aren't just random, they carry vital clues about the magnetic field that caused them. By closely analyzing how a signal is altered, scientists can figure out the strength and direction of the magnetic field it passes through. This makes radio signals valuable tools for studying magnetic fields across the universe. However, magnetic fields can also be problematic. They can interfere with signals, making them weaker or harder to detect. They can distort the signals, adding layers of complexity for scientists trying to interpret the data. This is why understanding magnetic fields is so crucial in radio astronomy. By learning how these fields affect radio signals, researchers can find ways to correct distortions and uncover the hidden information within the signals. Now, to see how magnetic fields shape environments that could support life, let's look closer to home. At Mars, the red planet in our cosmic neighborhood. Known for its massive volcanoes, deep canyons, and traces of ancient water, Mars has long fascinated scientists and dreamers alike. But unlike Earth, Mars holds a unique mystery tied to its magnetic environment, one that challenges our understanding of what makes a planet habitable. Mars has a weak and uneven magnetic field, which plays a big role in shaping its atmosphere and its ability to support life. Unlike Earth, whose magnetic field is powered by a spinning core, Mars' magnetic field is just a faint trace left in its crust. This leftover magnetism comes from a time long ago when the planet had a global magnetic shield. Without a strong magnetic field, Mars doesn't have a protective barrier to shield its atmosphere from the solar wind, a constant flow of charged particles blasting out from the sun. This exposure has had dramatic effects. New research led by R. Sakata from the University of Tokyo suggests that having a weak magnetic field, like Mars did after its core dynamo shut down, might cause the atmosphere to disappear even faster than if there were no magnetic field at all. Simulations show that a weak magnetic field can speed up atmospheric loss by up to 6 times compared to having no field. Here's why. The weak magnetic field lines are easily moved around by the solar wind, creating an open pathway for atmospheric particles to escape into space, especially on the side of Mars facing away from the Sun. Over billions of years, this process, called atmospheric stripping, caused Mars to lose most of its atmosphere. In its early history, Mars might have been a warm and wet world, with rivers, lakes, and perhaps even oceans. But as its magnetic field weakened and its atmosphere thinned, the planet turned into the cold, dry, and barren landscape we see today. This example from Mars shows how important magnetic fields are for a planet's ability to support life. Without a strong magnetic shield, even a planet that once had Earth-like qualities can lose the essentials for life, like air and water. Exoplanets, which are planets that orbit stars outside our solar system, have become a hot topic in astronomy. To date, more than 1,000 exoplanets have been discovered, offering us incredible opportunities to learn about the variety of planetary systems in our galaxy. One of the most thrilling breakthroughs in this field happened in late December 2021, when an international team of astronomers used the Hubble Space Telescope to make an exciting discovery. the first ever magnetic field detected on an exoplanet. This magnetic field was found on a planet called HP 111b, a Neptune-like planet located about 123 light-years away in the constellation Swan. HP 111b is classified as a hot Neptune. This means it's similar in size to Neptune, but orbits much closer to its star, making the planet's surface incredibly hot. At that time, the universe was so hot and dense that light couldn't travel freely. It was constantly scattered by charged particles. As the universe expanded, it cooled down enough for electrons and protons to combine and create neutral hydrogen atoms. This allowed light to escape, creating a blanket of radiation that fills the entire universe today. This radiation is no longer the intense heat it once was, but has stretched and cooled into microwave wavelengths due to the expansion of the universe. When we observe the CMB, we're essentially looking back in time, capturing a snapshot of the universe's infancy. This light provides crucial insight into the universe's age, composition, and structure. The relevance of CMB to universal boundaries lies in its uniformity and the tiny fluctuations present within it. These fluctuations represent the earliest seeds of all cosmic structure, galaxies, stars, and clusters. By studying these variations, scientists can infer the density and distribution of matter throughout the universe, helping them to establish models of how it has evolved over billions of years. Furthermore, the CMB acts as a boundary of sorts. It defines the observable universe, marking the limit beyond which we cannot gather information in a meaningful way. Anything beyond this cosmic horizon simply lies beyond our reach. Light from those regions of space has not had enough time to reach us since the birth of the universe. Thus, the cosmic microwave background not only serves as a relic from a pivotal moment in cosmic history, but also sets a physical boundary to our observations and understandings of the universe. Wormholes present fascinating challenges to our understanding of the universe and its boundaries. Traditionally, we picture the universe as expanding outward, with galaxies moving away from one another over vast expanses of space and time. This view holds that the edges of the universe are not physically defined. They represent regions beyond which we cannot see or travel due to the limitations of light speed. Now, imagine introducing a shortcut to this cosmic landscape. A wormhole would act like a bridge, connecting two points in space-time that are far apart. This means that, theoretically, one could traverse the universe much more quickly through a wormhole than following the traditional route through the vast emptiness between stars and galaxies. This possibility raises questions. If such shortcuts exist, what does it mean for the nature of distance and the ultimate edge of the universe? Conventional scientific theories posit that the universe is expanding uniformly. Yet, if wormholes were proven to exist, this could imply regions of space that are interconnected in ways we do not yet comprehend. The edges of the universe thus might not be as absolute as we thought. They could be penetrated or even bypassed. Current understanding suggests that nothing can travel faster than the speed of light, preserving the integrity of space-time. However, wormholes challenge this paradigm, suggesting a complex structure to the fabric of the universe that might permit instantaneous travel. The implications stretch beyond mere travel. They touch on critical concepts such as causality and the very nature of reality. For all the imaginative solutions wormholes offer, they also bring to light anomalies that conventional theories struggle to integrate. Thus, the existence of wormholes could force scientists to reconsider and expand upon our current models, reshaping what we understand about the universe's layout and edges. The concept of parallel universes opens up fascinating possibilities that can profoundly shape our understanding of the limits of the universe. Imagine a vast multiverse where every decision or event creates a branching path, leading to infinite variations of reality. Each of these realities exists independently, yet is influenced by the same foundational rules of physics that govern our own universe. When we consider parallel universes, we start to challenge the limitations we typically attribute to our understanding of existence. For instance, if multiple realities coexist, What does that mean for concepts like time, space, and causality? In our universe, we are constrained by certain physical laws, like the speed of light as a maximum speed limit or the singular nature of time flowing in one direction. But in a multiverse scenario, it's possible that different universes could operate under alternate physical laws or dimensions, stretching the very framework of what we deem possible. This idea encourages us to question the uniqueness of our own universe. If there are realities where fundamental forces behave differently or where time might loop back on itself, it begs the question of whether our current scientific laws are entirely universal or merely applicable to our specific universe. Each discovery we make in our universe could prompt a re-evaluation of those laws if we consider that other versions of reality might have discovered different truths. Ultimately, the existence of parallel universes suggests that the limits we perceive may only be the edges of our understanding. Expanding our perspective to include these alternate realities allows scientists to explore new theories, challenge long-standing assumptions, and approach the mysteries of cosmology and physics with greater imagination. Thus, parallel universes don't just challenge our understanding of the universe. They invite us to broaden our horizon of what is possible beyond the confines of our observable reality. Extra dimensions play a pivotal role in contemporary theories regarding the universe's structure. While we perceive the universe through three spatial dimensions, length, width, and height, some advanced scientific models suggest there could be additional dimensions beyond our immediate grasp. These dimensions can be thought of as hidden or curled up, existing at scales far smaller than we can observe with current technology. At the heart of these theories, like string theory, is the idea that the fundamental particles we observe are not simply point-like dots, but rather tiny, vibrating strings. The vibrations of these strings are influenced by the geometry of higher dimensions. Each configuration of these extra dimensions affects the physical properties of particles, such as their mass and charge, ultimately contributing to the richness of the universe we experience. The significance of these extra dimensions extends beyond mere speculation. They could help explain some of the universe's most profound mysteries. For instance, these theories might provide insights into the force of gravity as we know it, which remains weaker compared to other fundamental forces. By theorizing extra dimensions, scientists propose that gravity could be spilling into these additional dimensions, making it appear weaker in our three-dimensional experience. Furthermore, the shape of the universe might be influenced by these dimensions, potentially allowing for a more complex, multi-dimensional structure than the flat or curved spaces we can visualize. Understanding these dimensions helps physicists grapple with questions about the universe's early moments, black holes, and the integration of quantum mechanics with general relativity. Extra dimensions expand the framework within which we comprehend the universe. They offer a broader canvas for exploring fundamental forces, guiding researchers towards a deeper understanding of the very fabric of reality itself. Brain cosmology offers a unique perspective on the universe's structure by suggesting that our universe is not a standalone entity, but rather part of a larger framework. Imagine the universe as a vast sheet or membrane, commonly referred to as a brain, floating in a higher dimensional space. This brain represents our familiar three dimensions of space and one of time. Now, consider the idea that the edge of our universe isn't an absolute boundary, but rather a transition point where the brain can interact with additional dimensions or other brains. In this view, the edge isn't a solid wall where the universe abruptly ends. Instead, it might be a region where the laws of physics are fundamentally altered due to influences from these higher dimensions. These interactions could lead to fascinating phenomena, such as the creation of new universes or the potential for catastrophic events like collisions between brains. Such collisions could ripple through our universe, giving rise to bursts of energy that we might interpret as the origins of cosmic events, including the Big Bang itself. By incorporating higher dimensions into the fabric of existence, brain cosmology broadens our understanding of cosmic boundaries. Rather than a finite limit, the edge of the universe becomes a dynamic interface, hinting at a deeper and more complex reality beyond what we can see and measure, inviting exploration into a cosmos that is interconnected in ways we are only beginning to comprehend. Cosmic topology explores the shape and structure of the universe on a grand scale, asking questions about its overall form and configuration. When we refer to cosmic topology, we are essentially inquiring how the universe is connected and whether it has edges or boundaries at all. Imagine the universe as a three-dimensional shape, much like how a two-dimensional surface can be curved and connected in various ways. At one extreme, we could visualize a flat, infinite plane that stretches endlessly in all directions. In this scenario, there are no boundaries. You could travel forever without falling off an edge. On the opposite end, consider a finite structure like the surface of a sphere, where it is still possible to traverse the entire surface but always remain within its confines. As you move in one direction, you would eventually return to your starting point. Different models suggest various shapes for the universe, including toroidal forms, which resemble reshaped donuts, or even more complex structures. The intriguing aspect of cosmic topology is that it challenges our understanding of space itself. If the universe is indeed finite but without boundaries, it raises profound questions about what lies beyond our observable portion. Both cosmic topology and the laws governing the expansion of the universe influence our understanding of its composition and fate. This includes comprehending if the universe will continue to expand, collapse back in on itself, or stabilize in an eternal state. Ultimately, the concept of cosmic topology invites us to consider not just where the universe ends, but how it connects back to itself, creating a rich tapestry of cosmic architecture that remains one of the great mysteries of astrophysics. Observing the edge of the universe presents astronomers with a series of significant challenges, primarily rooted in the vastness and complexity of space. First and foremost is the sheer distance involved. The edge of the observable universe is so far away that the light reaching us from those regions began its journey billions of years ago. This journey means that we are looking into the distant past, making it challenging to understand how galaxies and cosmic structures evolve over time. Another substantial hurdle is the limitation of technology. Observational instruments, such as telescopes, require precise calibration and often rely on light across various wavelengths to detect objects. However, not all wavelengths can penetrate the Earth's atmosphere effectively, which restricts our ability to gather data from the universe's edges. Astronomers must place instruments in space to achieve a clearer view, yet maintaining and launching these instruments presents logistical and financial barriers. Furthermore, the expansion of the universe complicates the picture. The universe is not static, it is constantly expanding, and this expansion stretches the light from distant objects, causing what is known as redshift. This phenomenon can make distant objects harder to detect and requires sophisticated techniques to interpret the data correctly. Lastly, our understanding of cosmology itself is incomplete. Theories about dark matter and dark energy, which make up a significant part of the universe, are still developing. This lack of knowledge creates additional uncertainties in observations at the universe's edge. All these challenges underscore the complexity of peering into the vastness of space and highlight humanity's quest to unravel its mysteries. Cosmic phenomena, such as black holes, bring a fascinating complexity to our understanding of the cosmos and what lies beyond universal borders. To imagine a black hole, consider the idea of a region in space where the gravitational pull is incredibly strong. It is so intense that nothing can escape it, not even light. This creates an area known as the event horizon, which acts like a boundary, and once crossed, all information about what goes in appears lost to the outside universe. This loss of information challenges our fundamental ideas about the universe. We often think of space as a vast expanse with well-defined edges, but black holes invite us to reconsider how we view these limits. They suggest that there are regions within the universe where conventional rules no longer apply, complicating our notions of boundaries. The incredible gravitational forces can warp both space and time, bending the fabric of reality itself. The presence of black holes affects how matter and energy behave near them, leading to questions about the very nature of the cosmos. For instance, if material falls into a black hole, does it simply vanish, or is it transformed in ways we do not yet comprehend? The theories we rely on to understand these phenomena, such as the principles of relativity, become increasingly difficult to apply in the presence of such extreme conditions. Furthermore, the study of black holes intersects with questions surrounding the ultimate fate of the universe. As these entities grow by consuming surrounding matter, they can challenge existing theories about the formation of galaxies and the evolution of cosmic structures. Thus, black holes do more than just exist in the universe. They present a puzzle that invites us to explore the boundaries of our understanding and encourages scientists to develop new theories that might better describe our strange and complex reality. In this way, cosmic phenomena force us to reconsider not just the edges of our universe, but the very laws that govern its existence. The discovery of exoplanets, or planets beyond our solar system, has profoundly transformed our understanding of the universe. For centuries, astronomers focused primarily on our own celestial neighborhood. The planets, moons, and other bodies within our solar system seemed to represent the entirety of what was possible in the cosmos. But the identification of exoplanets shifted that perspective dramatically. Imagine peering into a vast ocean and believing your little pond contained all there was to see. When exoplanets began to be detected, it was like discovering that the ocean was teeming with life and diversity far beyond the confines of your pond. Each confirmed exoplanet brings with it unique characteristics. Some are massive gas giants, while others are rocky, Earth-sized bodies that might support life. This discovery has inspired new questions, such as what conditions are necessary for life to arise, and whether other worlds could harbor intelligent civilizations like our own. Moreover, the methods used to detect exoplanets, such as observing the dimming of a star's light when a planet passes in front of it, have opened up new avenues of inquiry. Now, astronomers can study the atmospheres of these distant worlds, searching for chemical signatures that might indicate the presence of water or even signs of life. This quest has led to a more dynamic and comprehensive approach to studying the universe, focusing not just on the stars and planets themselves, but also on the possibilities they represent. The implications extend beyond individual discoveries. They encourage collaboration across different fields of science. Astrophysicists, planetary scientists, and even biologists are engaging in interdisciplinary studies to understand not only how these planets form, but also how they might evolve and what they could mean for the future of humanity. The search for exoplanets has shifted our focus from a narrow view of our solar system to a broader understanding of a diverse, dynamic universe, rich with possibilities. The excitement of exploring these new worlds fuels our curiosity and drives fundamental questions about our place in the cosmos. The universe is no longer just a backdrop for human existence, it is a playground for discovery, one that holds the secrets to life and beyond. The Hubble Space Telescope plays a crucial role in our quest to understand the vastness of the universe. Positioned far above the Earth's atmosphere, this remarkable instrument has a clear view of the cosmos, free from the blurring effects caused by air. Through its powerful lenses, Hubble captures stunning images and collects data that reveal the intricacies of distant galaxies, stars, and other celestial phenomena. One of Hubble's key contributions is its ability to peer deep into space and time. By observing light that has traveled for billions of years, Hubble allows scientists to witness the formation and evolution of galaxies as they were in the early universe, providing a glimpse into conditions that prevailed shortly after the Big Bang. This capability helps researchers ascertain the age and the rate of expansion of the universe, shedding light on fundamental questions concerning its origin and destiny. Moreover, Hubble has been instrumental in identifying distant exoplanets, planets orbiting stars other than our own. By analyzing starlight that passes through the atmospheres of these exoplanets, Hubble helps scientists detect chemical signatures that may indicate the potential for life beyond Earth. Its observations also contribute to our understanding of black holes, as Hubble can observe how these enigmatic entities affect nearby stars and gas. Through ongoing collaboration with other telescopes and observatories, Hubble's data continues to refine our models of cosmology. Each new discovery not only answers existing questions, but also raises new ones, pushing the boundaries of our knowledge further outward. The Hubble Space Telescope acts as a bridge between our current understanding and the unknown, illuminating the universe's limits while encouraging exploration beyond them. Cosmic censorship theory delves into the enigmatic relationship between black holes and the limits of our understanding of the universe. At its core, the theory posits that certain cosmic events, particularly those involving black holes, should not lead to observable inconsistencies in the fabric of space-time. In simpler terms, it suggests that any singularities, points in space where gravitational forces become infinite, are hidden from view, surrounded by event horizons that obscure them from our perception. Imagine looking at the surface of a calm lake, where the water is still and everything appears normal. If something disrupts that calm, like a stone being thrown, ripples begin to spread out, distorting the surface. Similarly, when it comes to black holes, these singularities create a tremendous distortion in space-time. According to cosmic censorship, this distortion is effectively cloaked. The event horizon acts like a barrier, preventing any information about the singularity from escaping. As a result, we are unable to observe the regions of extreme gravity and the chaotic nature of space-time within black holes. This has profound implications for our understanding of the universe's boundaries. It suggests that the universe contains realms that could potentially be disconnected from our observable reality. If true, cosmic censorship reinforces the idea that while we can study the structures and dynamics of galaxies, stars, and other celestial objects, there are limitations on what we can ultimately know about the most extreme phenomena. These hidden realms challenge our capacity to gather complete information about the cosmos, reminding us that there are still many mysteries tightly woven into the very fabric of space-time. Thus, cosmic censorship not only shapes our theories about black holes, but also highlights the boundaries of human knowledge regarding the universe itself. Current space telescopes, while advanced and capable of remarkable discoveries, face several observational limitations that can affect their ability to capture the full scope of the universe. Firstly, one primary constraint is their field of view. Many telescopes are designed for detailed observations of specific areas, which means they might miss wider phenomena that occur outside their immediate range. This limitation requires repeated observations over time to stitch together a more comprehensive picture of the cosmos. Another consideration is the sensitivity of these instruments. Telescopes rely on collecting light from distant objects, and their ability to do so can be hampered by factors such as interference from cosmic dust or background light from stars and galaxies nearby. This background can overwhelm the faint signals of more distant celestial bodies, making them difficult to observe. Moreover, the wavelengths of light that telescopes are able to detect define their observational range. Most space telescopes are optimized for specific parts of the electromagnetic spectrum, such as visible light or infrared, which means they may overlook valuable information captured in other wavelengths, like X-rays or radio waves. Understanding the universe fully requires integrating data across these various forms. Another critical factor is the telescope's orbit and position. While being above Earth's atmosphere reduces atmospheric interference, telescopes located in low Earth orbit remain susceptible to light pollution from urban areas when they are not properly shielded. Further, telescopes in orbits that are not perfectly stable can experience disruptions that affect their ability to track celestial objects over time. Lastly, technological limitations can hinder observational capabilities, including issues with resolution and the effects of cosmic rays, which can interfere with data collection and analysis. The complexity of processing the vast amounts of data generated also poses challenges, requiring innovative methods and computational resources to extract meaningful insights. While space telescopes are powerful tools for exploring the universe, factors such as limited fields of view, sensitivity to light, wavelength constraints, orbital challenges, and technological limitations all contribute to the complexities of space observation. Each of these elements plays a crucial role, shaping what we can discern about the cosmos and highlighting the need for continued advancements in telescope technology and design. Cosmic rays are high-energy particles that travel through space and can reach Earth from all directions. To understand how they help us glean information about the edge of the universe, imagine these particles as messengers from the far reaches of space. They originate from various sources, including supernova explosions and active galactic nuclei, extremely energetic centers of distant galaxies. When cosmic rays travel through the universe, they interact with magnetic fields and other particles. This journey can change their direction and energy, acting like a cosmic GPS system. By studying how these particles arrive at Earth, scientists can infer details about their origin and the environments they traveled through. The characteristics of cosmic rays, such as their energy distribution and composition, reveal crucial information about the conditions in space, including the presence of magnetic fields and the density of intergalactic matter. Specifically, cosmic rays can indicate the presence of regions where energetic events occur, suggesting the boundaries of our universe and potentially the structures that define it, such as galaxy clusters. Moreover, cosmic rays can help us indirectly probe the nature of dark matter, an elusive substance that makes up a large portion of the universe. By examining the patterns in cosmic ray arrivals, researchers gain insights into how dark matter interacts with particles, thus offering a glimpse into the universe's composition and the forces at its edges. Through ongoing research, cosmic rays serve as a valuable tool for expanding our understanding of our cosmic environment, unveiling the mysteries that exist at the very limits of our universe. Cosmic background noise poses significant challenges to scientists trying to study the universe. To visualize this, think of cosmic background noise as a clutter of static and whispers that blend into the rich symphony of the cosmos. This noise primarily comes from remnants of the Big Bang, known as the cosmic microwave background radiation, which radiates uniformly throughout space. While this ancient radiation is essential for understanding the early universe, it can be overwhelming. One of the main difficulties lies in separating the signals scientists want to detect from this pervasive noise. Imagine trying to listen to a faint conversation while a loud crowd is cheering nearby. In the vastness of space, measurements can be distorted by many factors, including this background noise, which hampers the detection of weaker signals from distant galaxies or unseen dark matter. Moreover, the instruments that scientists use to observe the universe, such as telescopes, can also introduce their own noise. Just like an old radio may produce additional crackling sounds, telescopes can generate unwanted signals from their electronic systems or from ground-level sources, which mix with the cosmic noise, further clouding the data being collected. To mitigate these issues, researchers employ advanced techniques such as signal processing methods to filter out the noise and extract meaningful information. This requires not only complex algorithms, but also a deep understanding of both the desired signals and the noise they must contend with. Ultimately, navigating through this cosmic cacophony is crucial for unlocking the mysteries of the universe and gaining insight into its formation and evolution. Gravitational waves are ripples in the fabric of space-time, produced by some of the most violent and energetic processes in the universe, such as colliding black holes or neutron stars. Imagine dropping a stone in a pond and watching the waves ripple outward. In a similar way, these gravitational waves spread out through space, carrying crucial information about their origins. When these waves traverse the universe, they can pass through matter almost undisturbed, providing a unique glimpse into events that might otherwise be hidden from view. This ability to travel through obstacles like stars and galaxies allows scientists to study phenomena that are difficult to observe through traditional means, such as light. By detecting these waves, researchers can infer the properties of the massive objects that created them, such as their masses, spins, and distances. Understanding the patterns and characteristics of these waves helps astronomers piece together the behavior of the universe itself. For example, by analyzing the waves resulting from a black hole merger, scientists can learn about the formation and evolution of black holes, challenging existing theories about how they develop. Furthermore, gravitational waves provide insights into the expansion of the universe by revealing details about its rate and history. This new avenue of cosmic investigation opens doors to studying aspects of the universe that we may not yet fully understand, such as the inner workings of neutron stars or even the elusive nature of dark matter. Gravitational waves serve as a cosmic messenger, telling us about the structure of the universe in ways that light cannot, enriching our understanding of the cosmos and answering fundamental questions about its nature. Gamma-ray bursts are among the most powerful explosions in the universe, often regarded as cosmic beacons that guide scientists into the depths of space exploration. These bursts emit an immense amount of energy across a wide spectrum, with gamma rays at the forefront. Imagine them as flashes of light that occur when massive stars undergo cataclysmic collapses, leading to supernovae, or when two dense neutron stars collide, creating a surge of energy that outshines entire galaxies for brief moments. The significance of gamma-ray bursts lies in their incredible luminosity. They can be observed from vast distances, making them visible even billions of light-years away. This allows astronomers to peer deeper into the universe's history than with many other astronomical phenomena. As these bursts occur in regions that may be far removed from our own galaxy, they act like lighthouses, illuminating the distant cosmos and providing insights about the conditions of the early universe. Furthermore, the study of gamma-ray bursts has immense implications for understanding cosmic structures and processes. By analyzing the light emitted from these events, scientists can learn about the composition and behavior of the interstellar medium where the bursts occur. This information unveils details about star formation, the life cycle of stars, and the evolution of galaxies. In a broader context, gamma-ray bursts challenge our understanding of fundamental physics as they push the limits of what we know about gravity, matter, and energy. They inspire technological advancements as researchers develop tools and methods to detect and interpret the signals coming from these distant explosions. As instruments become more sophisticated, our exploration boundaries expand, revealing the universe's mysteries and enriching our comprehension of cosmic phenomena. The dance of light from gamma-ray bursts isn't just a spectacle, it actively shapes our quest for knowledge about the universe we inhabit. The Oort cloud can be envisioned as a vast, spherical shell surrounding our solar system, acting as a boundary to our current understanding of where our cosmic neighborhood ends. Picture a swarm of icy bodies lingering far beyond the orbit of the most distant planets, like an invisible fence marking the edge of the solar system. This region, believed to be teeming with comets and other frozen remnants from the solar system's formation, helps frame the way we think about what lies beyond our immediate solar system. Although we have not directly observed the Oort cloud, scientists infer its existence from the behavior of long-period comets that seem to originate from this distant realm. These comets occasionally venture inward toward the Sun, providing glimpses of the material that may lie in that far-off zone. The Oort cloud symbolizes more than just a boundary. It challenges our perception of the universe's edge, suggesting that the solar system is not an isolated entity, but part of a much larger and more complex cosmic environment. This distant region raises intriguing questions about what else might exist beyond our view in the vastness of space. It represents the frontier of our solar system's influence, hinting at the possibility of more mysterious phenomena, including distant star systems and hidden celestial bodies yet to be discovered. Instead of seeing the universe as a finite space, the Oort cloud encourages a perspective of endless possibility, inspiring scientists and dreamers alike to ponder the unknown expanses that remain just beyond our reach. Quantum mechanics plays a pivotal role in shaping our understanding of the universe, especially when delving into its most extreme aspects. To grasp this, consider that at the very smallest scales of reality, particles behave not just like solid objects, but exhibit wave-like properties, blurring the lines of conventional behavior. This foundational principle leads to phenomena that appear strange and counterintuitive, altering how we understand everything from the fabric of space-time to the very nature of energy. In areas such as black holes and the Big Bang, quantum mechanics introduces concepts like uncertainty and superposition, which challenge classical ideas of determinism. For instance, within a black hole, gravity compresses matter to an unimaginable extent, creating an environment where quantum effects cannot be ignored. Theories suggest that near the event horizon, the boundary beyond which nothing can escape, quantum fluctuations allow particles to pop in and out of existence, which could lead to the creation of new universes or the information paradox, a mystery surrounding what happens to information swallowed by black holes. Moreover, when we explore the early universe during the moments of the Big Bang, quantum mechanics provides insights into how particles interacted at incredibly high energies and densities. Quantum fluctuations may have been responsible for the seeds of structure in the universe, leading to galaxies and clusters. These tiny variations in energy density, ripples in the fabric of the early universe, could have served as the starting point for everything we observe today. The interplay of quantum mechanics with cosmic phenomena unveils a landscape filled with bizarre yet essential concepts, challenging our perceptions and guiding theories about the extremes of space and time. It suggests that to truly understand the universe, one must embrace the weirdness of the quantum realm, where the conventional rules simply do not apply, revealing a more complex and interconnected reality. String theory introduces a fascinating idea that goes beyond traditional concepts of how we understand the universe. Traditionally, we think of the universe as being composed of point-like particles, which are the building blocks of all matter. However, string theory proposes that these particles are not simply points, but rather tiny, vibrating strings. Imagine these strings as miniature rubber bands oscillating at different frequencies. The way they vibrate determines the properties of the particles we observe, such as their mass and charge. This perspective has profound implications, especially when we consider the edges of our universe. While we often view the universe as a vast, three-dimensional space, string theory hints at the possibility of more dimensions hidden from our senses, perhaps up to 10 in total. These additional dimensions might shape the nature of the universe's edge. Rather than a simple boundary or an abrupt end, the edge could function more like a portal or a gateway to these unseen realms. This challenges our conception of an end and suggests that what lies beyond our observable universe could be interwoven with higher dimensions, affecting how we experience reality itself. Furthermore, string theory encourages us to think about the universe in terms of interconnectedness. Such a framework implies that the universe is not just an isolated entity, it is part of a larger, more intricate, multidimensional structure. This understanding might redefine what we consider the edge of the universe, as it blends the known with the unexplored, suggesting a limitless expanse of possibilities that extend beyond our current grasp. Thus, while traditional notions of the universe's edge imply a finality or termination, string theory proposes a more fluid and interconnected perspective, one where boundaries dissolve and the cosmos is part of a vibrant tapestry of dimensions yet to be fully understood. The holographic principle is a fascinating theory that proposes that all the information contained within a volume of space can be represented as a two-dimensional surface, much like a hologram. Imagine a three-dimensional image projected from a flat surface. Similarly, this principle suggests that our entire universe, with all its complexities and dimensions, might be fundamentally encoded on a two-dimensional boundary, such as the surface of a black hole. This concept challenges our traditional understanding of space and dimensions. It implies that the laws of physics, as we know them in three dimensions, can be derived from phenomena occurring on this two-dimensional plane. If we think of the universe as having limits, the holographic principle provides a framework to explain how all the vast information can fit into a seemingly smaller set of data. It posits that the intricate details of our three-dimensional existence aren't inherently contained in space itself, but rather emerge from a more fundamental layer that could be extending far beyond our perception. Furthermore, this principle addresses questions about what lies at the edges of the universe. If space can be reduced to information on a surface, this could suggest that at some level our observed universe is confined or bounded, perhaps explaining phenomena like the cosmic horizon. It raises profound implications on the nature of gravity, black holes, and the fabric of space-time itself. In exploring these boundaries, the holographic principle offers a glimpse into the possible limits of the universe and invites us to rethink how we understand reality at its most fundamental level. The simulation hypothesis suggests that our reality might not be the original one, but rather a sophisticated simulation created by an advanced civilization. This idea often prompts discussions about the nature of consciousness, existence, and the universe itself. When we consider this hypothesis in the context of universal edge theories, the perspective broadens significantly. Universal edge theories propose that there are boundaries or limits to our understanding of the universe, including the laws of physics as we know them. Imagine a vast ocean where the shore represents the limits of our knowledge. Beyond that shore lies the unknown, and the simulation hypothesis invites us to consider: what if our perceived universe is just a small part of a grander reality, orchestrated by entities capable of manipulating those very boundaries? If we view our universe as a simulation, those edges might not represent the ultimate constraints, but rather the programmed rules within this artificial environment. The laws of physics might be like the rules in a game, defining how players interact within a specific context, but potentially modifiable if the game's creators so choose. This introduces tantalizing questions about what lies beyond our limited perspective. Additionally, some interpretations of the simulation hypothesis suggest that just as computer simulations can vary widely in complexity and rules, the universe itself might have layers. Each layer could represent different simulations or realities, interwoven with one another. Universal edge theories then become tools that help us speculate about what exists beyond the simulation we experience, leading to ideas about parallel worlds, alternate dimensions, or even other forms of existence that we cannot yet comprehend. Marrying the simulation hypothesis with universal edge theories compels us to rethink our assumptions about reality, our place within it, and the potential for other realms beyond our everyday existence. It challenges us to consider whether what we perceive is mere data running through a program designed for exploration, understanding, or perhaps other purposes we have yet to uncover. The anthropic principle presents a fascinating insight into our existence within the cosmos. At its core, this principle suggests that the universe's fundamental properties are finely tuned to allow for the emergence of conscious beings capable of observing and reflecting on it. Picture the universe as the ultimate stage, where certain conditions must be just right for life to flourish. This concept implies that if the fundamental forces of nature or the values of various constants were even slightly different, life as we know it might not have emerged at all. This notion shifts our understanding of the universe from one purely focused on natural laws to a perspective that incorporates the role of observers. It invites the question, why is the universe as it is? The anthropic principle can be viewed through two lenses, weak and strong. The weak version merely asserts that our universe must allow for life to exist, since we are here to observe it. In contrast, the strong version suggests that the universe exists in such a way precisely because it must support conscious observers. When we explore the significance of the anthropic principle, we recognize its implications for cosmology and the study of fine-tuning. Some scientists posit that an infinite number of universes may exist, each with differing laws and conditions. Within this multiverse theory, it's not surprising we find ourselves in a universe capable of supporting life, as this is simply one of many realms. The principle also encourages deeper inquiry into the nature of existence itself, compelling us to examine the boundaries between science, philosophy, and our place in the grand tapestry of reality. Ultimately, it broadens our perspective, suggesting that the universe may not just be a cold, indifferent expanse, but a domain where consciousness plays a pivotal role. Speculative technologies like warp drives ignite fascinating discussions about the boundaries of our universe. A warp drive, conceived in theoretical physics, proposes a method of faster-than-light travel by manipulating space itself. Imagine a bubble of distorted space around a spacecraft, allowing it to travel vast cosmic distances by contracting space in front and expanding it behind. This concept challenges traditional ideas about the speed limits of travel set by the laws of physics. The implications of such technology stretch far beyond just quicker journeys. If a warp drive could be realized, it could transform our understanding of the universe's structure and limits. Scientists currently believe the universe is finite and ever-expanding, with galaxies receding from one another. Yet, the introduction of warp drives might suggest that intergalactic travel could make parts of the universe more accessible than previously thought. This could lead to theoretical re-evaluations of what constitutes the edges of the universe. Moreover, warp drives would invite exploration into realms beyond known physics. These machines could theoretically allow humanity to cross regions of space that appear unreachable under conventional travel methods, encouraging a re-evaluation of cosmic geography. This re-evaluation could alter our studies of celestial phenomena, allowing us to gather data from previously inaccessible areas of the cosmos. However, while warp drive technology remains speculative, it raises critical questions about causality, space-time, and the fundamental nature of reality itself. If such travel were to become feasible, it would not only redefine our navigation through the universe, but could potentially challenge the very principles that govern physics, urging a more profound inquiry into the structure of existence. Tachyons are hypothetical particles that challenge our conventions of speed and movement. These particles, if they exist, would always travel faster than light. To understand the implications of tachyons, it's essential to grasp how they differ from ordinary particles. Regular particles, like those that make up everyday matter, increase their mass as they approach the speed of light. However, tachyons would exhibit the opposite behavior. Their mass would decrease as they accelerate, allowing them to surpass light speed. The existence of tachyons could offer unique insights into realms beyond our universe, often referred to as the multiverse. If tachyons exist and can traverse these dimensions faster than light, they could potentially provide information about regions and realities outside our observable universe. Theoretically, they would carry signals or data across vast distances almost instantaneously, bridging gaps that regular particles cannot. This characteristic raises fascinating questions about the structure of spacetime itself. If we could detect tachyons or their influences, we might gain clues about the fundamental nature of reality, perhaps hinting at the existence of alternate universes, or shedding light on the early moments of the universe before light could travel freely. While tachyons remain a speculative idea, they open intriguing theoretical pathways that could expand our understanding of what lies beyond the known cosmos and reshape our perspective on the very fabric of existence. Time dilation and relativity play critical roles in our understanding of the universe, especially when we consider speculative theories about its vastness and possible limits. At the heart of Einstein's theory of relativity is the idea that time is not a constant. Instead, it varies depending on how fast an object is moving and its position in relation to gravitational fields. Imagine a spacecraft racing through the cosmos at a significant fraction of the speed of light. For the astronauts aboard, time would pass normally, but for those left on Earth, years could tick by rapidly. This phenomenon, known as time dilation, illustrates that the faster you travel, the slower time moves for you compared to someone stationary. It raises fascinating questions about what our universe might hold beyond what we perceive. Considering these concepts leads to intriguing possibilities. The vast distances in space mean that light from distant galaxies has been traveling for billions of years. If someday humanity finds a way to achieve near light-speed travel, the implications are profound. Explorers could experience a relatively short journey while potentially witnessing the unfolding of cosmic history that others on Earth experience over much longer time spans. Furthermore, the notion of relativity suggests that what we deem as the edge of the universe may be more fluid than it appears. The universe is constantly expanding, and if time itself behaves differently under various circumstances, it opens the door to discussions about multiverses and dimensions beyond our current understanding. Time dilation serves not just as a scientific curiosity, but as a gateway to speculative theories about the universe's reach and the possibility that there could be much more beyond the constraints of our perception. An invitation to explore not just space, but the very nature of existence. As we stand on the brink of a new era of exploration, future technologies could dramatically enhance our understanding of the universe's boundaries. Imagine sophisticated telescopes equipped with advanced sensors that can capture light from the farthest reaches of space, delving into areas of the cosmos that are currently beyond our reach. These instruments would not only allow us to see further, but also to gather data across different wavelengths of light, revealing secrets hidden from our current observational prowess. With the advent of more powerful computers and artificial intelligence, analyzing the vast amounts of data collected will evolve beyond traditional methods. AI could discern patterns and anomalies in cosmic background radiation or other phenomena, unveiling clues about the universe's structure, its expansion, and perhaps even its ultimate fate. This capability would transform our approach to cosmology, allowing us to refine our models of how galaxies form, collide, and interact throughout their lifespans. Also, advancements in space travel technologies could pave the way for human-made probes to venture into the unseen territories of the universe. Such missions could provide direct measurements and experiences in environments never before encountered, offering first-hand insights into cosmic phenomena. Imagine a probe that could traverse the space between galaxies, gathering data about the intergalactic medium, dark matter, and the influence of cosmic radiation on the structure of the universe itself. In addition, technologies such as gravitational wave detectors could unveil aspects of the cosmic landscape that emit no light at all. As these instruments become more sensitive, they could detect the ripples in space-time caused by massive cosmic events, helping us understand the dynamics of black holes or the collision of neutron stars, expanding our comprehension of the universe's edges. Overall, these emerging technologies promise not just to enhance our knowledge, but also to challenge our existing frameworks and theories about the universe. The boundaries of what we understand may shift as we unlock new dimensions of information, turning our gaze toward the cosmos with renewed curiosity and insight. The universe is full of profound mysteries, especially when we consider its boundaries. One of the most intriguing questions concerns the universe's expansion. Just as a balloon stretches as it inflates, the universe is expanding, pushing galaxies away from each other. However, observations show that this expansion is accelerating. What drives this mysterious force, often referred to as dark energy, remains a puzzle. It constitutes much of the universe's makeup, yet we know little about its true nature. Another captivating mystery involves the concept of the observable universe itself. Beyond what we can see lies a vast expanse of space that is not directly observable. Due to the finite speed of light, we can only view light that has had time to reach us since the universe began. This creates a cosmic horizon, a limit to our knowledge. What lies beyond this horizon is unknown, and some theorists suggest it could harbor structures or phenomena that defy our current understanding of physics. Then there's dark matter, an unseen form of matter that does not emit light or energy. It is detectable only through its gravitational effects on visible matter. Its existence hints at a hidden layer of the universe that remains elusive. This dark matter makes up a significant portion of the universe, influencing the formation of galaxies and the cosmic web we see today, yet its exact nature is still undefined. Adding to these mysteries is the question of whether our universe is just one of many. The multiverse theory proposes that there might be other universes, each with different physical laws and constants. If true, this would fundamentally shift our understanding of existence, placing our universe in a broader context. These cosmic mysteries reflect the limits of our knowledge, drawing scientists ever closer to the edge of understanding. Each exploration not only seeks to unveil these secrets, but also reshapes our perception of what the universe truly is, constantly reminding us that there is still so much left to discover. Unexplained phenomena have long served as catalysts for scientific inquiry, pushing the boundaries of our understanding of the universe. Imagine standing at the edge of a vast ocean where the horizon seems endless. Just as sailors were often motivated to explore beyond the horizon, scientists are driven to investigate the mysteries that linger in the cosmos. These phenomena, from dark matter and dark energy to gravitational waves, challenge the current frameworks and compel researchers to rethink what they know about the universe. For instance, dark matter, an invisible substance that does not emit light or energy, has been inferred through its gravitational effects on visible matter. This has led to the realization that what we can see is just a small portion of the universe's total mass. As a result, theories now expand beyond ordinary matter, incorporating strange and elusive components that shape cosmic structures. Similarly, dark energy, which seems to be responsible for the accelerated expansion of the universe, suggests that we may not fully grasp the nature of space itself. This driving force challenges the notion that gravity, which pulls objects together, is the only significant player. Instead, our comprehension of the universe's fabric must adjust to account for these powerful, unseen influences. Gravitational waves, detected through their minute ripples in space-time, have opened new avenues for understanding cosmic events such as black hole mergers and neutron-star collisions. These discoveries remind us that the universe is dynamic and filled with interactions that can reshape existing theories. Each of these enigmatic phenomena influences theoretical boundaries, urging scientists to delve deeper, whether by proposing new models or re-evaluating existing ones. This ongoing investigation reflects humanity's insatiable curiosity and highlights a reality where the universe remains an ever-expanding puzzle. It's through these mysteries that our understanding stretches across time and space, continually redefining what we think we know about the cosmos. Astronomical anomalies, those unexpected or unexplained phenomena in the cosmos, serve as crucial puzzle pieces that can upend established theories about the universe. When astronomers observe something that doesn't fit the expected patterns, like stars behaving strangely or galaxies displaying unusual distributions of mass, they are confronted with the limitations of their current understandings. These anomalies prompt scientists to dig deeper, forcing a re-evaluation of existing concepts. Take dark matter, for instance. It was proposed to account for the mass discrepancies seen in galaxies. When scientists noted that these celestial bodies spun at such speeds that they should, logically, tear themselves apart, they introduced the idea of an unseen substance providing the necessary gravitational pull. Yet, the exact nature of dark matter remains elusive, with many anomalies hinting that perhaps the universe operates under different rules than we currently comprehend. Similarly, observations of rapid expansion in the universe led to the concept of dark energy, which represents another significant anomaly. The pressing question arises: why is the universe expanding faster now than it did in its earlier stages? This counters conventional ideas that gravity should slow that expansion over time. Such evidence reshapes our understanding, suggesting that there are invisible forces at play that we have yet to fully understand. Each anomaly acts as a catalyst for innovation, urging scientists to develop new theories or modify existing ones. As researchers confront these mysterious phenomena, they explore concepts like quantum physics, altered gravitational laws, or new dimensions of space. In this way, anomalies don't just challenge our understanding, They pave the way for breakthroughs, inspiring questions that broaden the horizons of cosmic knowledge and pushing the boundaries of science further into the unknown. Ultimately, they remind us that the universe is vast and full of surprises, often leading us to discover more than we ever thought possible. At the boundaries of our understanding, where the universe presents its most perplexing phenomena, scientists face the challenge of reconciling theoretical predictions with observed reality. When observations contradict established theories, such as those regarding the behavior of distant galaxies or cosmic events, scientists undertake an intricate process of investigation. First, they examine the data rigorously, ensuring that the observations are accurate, reliable, and free from interference. Advanced technologies and methods, including sophisticated telescopes and computer simulations, help to refine the information they gather. This meticulous scrutiny is essential. Sometimes the contradiction arises from a simple error in measurement or data interpretation. When data integrity is confirmed, scientists revisit the theoretical framework that produced the conflicting predictions. They might consider whether adjustments or enhancements to the existing theory could resolve the dilemma. This iterative process often leads to modified or entirely new models that better account for the observed phenomena, illustrating the dynamic nature of scientific inquiry. In cases where contradictions persist, they may prompt a paradigm shift, leading scientists to develop novel theories that challenge our fundamental understanding of the universe. For instance, the discovery that the universe is expanding at an accelerating rate led to the introduction of dark energy as a new concept, revolutionizing cosmological theories. Ultimately, scientists engage in dialogue, sharing findings and encouraging collaboration across the global research community. This collective effort fosters creativity and innovation, enabling researchers to explore alternative explanations and blend insights from various fields. In this way, contradictions between theory and observation at the universe's edge not only deepen our understanding, but also drive the pursuit of knowledge further into the cosmic unknown. Deep space phenomena act as portals to understanding the universe's complexities. Observations of distant galaxies reveal a vast tapestry woven with threads of cosmic events that date back to the universe's infancy. For instance, studying the light from these ancient galaxies provides insights into their formation and evolution, highlighting the intricate processes that have shaped them over billions of years. One of the most compelling mysteries illuminated by deep space observations is the existence of dark matter. While it cannot be seen directly, its presence is inferred through the gravitational effects it exerts on visible matter. This has led scientists to speculate about the nature of this unseen substance, which appears to make up a substantial portion of the universe, fundamentally altering our understanding of gravity and structure formation. Similarly, the discovery of cosmic microwave background radiation, a remnant from the early universe, has given researchers a glimpse into the conditions that existed just moments after the Big Bang. This faint glow provides critical data supporting the Big Bang theory, revealing that the universe began in a hot, dense state and expanded over time, cooling and evolving into the cosmos we see today. The phenomena of supernovae, the explosive deaths of massive stars, play a key role in revealing the distribution of elements throughout the universe. These events not only create and scatter heavy elements, but also serve as standard candles for measuring cosmic distances, allowing scientists to map the expansion of the universe and the mysterious acceleration that seems to drive it. Additionally, observations of gravitational waves from colliding black holes and neutron stars have opened a new chapter in understanding the universe. They confirm predictions of Einstein's theory of general relativity, while presenting an entirely new way to gather information about cosmic events that were previously undetectable. Thus, the study of deep space phenomena continues to peel back the layers of the universe's mysteries, from the nature of dark matter and energy to the formation of cosmic structures. Each observation adds pieces to an ever-expanding puzzle, fueling humanity's quest to comprehend our existence within this vast and largely unknown cosmos. Quasars, short for quasi-stellar objects, are among the brightest and most energetic entities in the universe. They serve as remarkable cosmic beacons, illuminating our understanding of extreme conditions and events in the universe. At their core, quasars are powered by supermassive black holes that reside at the centers of distant galaxies. As surrounding gas and dust swirl into these monstrous black holes, they are heated to incredible temperatures, producing vast amounts of energy that can outshine entire galaxies. One of the most profound contributions of quasars to our understanding is their role in probing the early universe. Many of the quasars we observe today emitted their light billions of years ago, which allows astronomers to glimpse how galaxies evolved shortly after the Big Bang. By studying the light from these distant quasars, we can uncover details about the composition of the universe at that time, including how matter was distributed and how the early galaxies and stars formed. Moreover, quasars are instrumental in exploring the fundamental laws of physics under extreme conditions. The immense gravitational and energetic forces that surround a quasar can lead to phenomena not easily observed elsewhere. For instance, they provide insight into the behavior of matter and radiation in environments where gravity is extraordinarily strong, which can test our understanding of general relativity and the limits of known physics. Quasars also offer valuable information about the expansion of the universe. By measuring their light across vast distances, scientists can calculate how quickly the universe is expanding and the rate at which it has changed over cosmic time. This can lead to conclusions about dark energy, a mysterious force that seems to be accelerating this expansion. By observing and studying quasars, we not only appreciate some of the most extreme environments in the universe, but also gather crucial clues about the universe's origins, evolution, and the fundamental forces that govern it. These fascinating objects illuminate paths to knowledge, pushing the boundaries of what we understand about space and time itself. Discovering nothingness at the edges of the universe would lead to profound implications for our understanding of existence and the cosmos. When we speak of nothingness in this context, we are referring to the absence of matter, light, and even the usual forces that shape our cosmic environment. This idea challenges our fundamental beliefs about how the universe operates and what it means to be a part of it. First, if regions of nothingness exist, it could imply that our universe is not a solitary entity, but rather a part of a larger multiverse, a collection of universes each with different properties and behaviors. This leads to the tantalizing question of whether these other universes are even accessible, or if they remain forever out of reach, shrouded in the vast void that separates them. Second, encountering nothingness might reshape our understanding of the cosmos's evolution. It could suggest that the universe we observe is merely a phase in a more extensive cycle of expansion or contraction, a chapter in an ongoing cosmic narrative. This could challenge the current models of cosmology that depict the universe as an ever-expanding entity from a singular beginning. Moreover, if we consider nothingness, it may also require us to rethink the very fabric of reality. Traditional concepts of space and time, which we use to navigate our understanding of the universe, might not apply at these edges. It could reveal that our perception of the universe's boundaries is far more fluid than we suppose, leading to existential questions about the nature of space itself. Finally, this discovery could ignite philosophical debates on the meaning of existence. If parts of the universe exhibit absolute nothingness, what does that signify for life and consciousness? Is existence precious because it is juxtaposed against the backdrop of nothingness? Such revelations could deepen our introspection about our place in the cosmos, pushing us to grapple with profound questions that blend science with philosophy. Discovering nothingness at the universe's borders could redefine everything we thought we understood about reality itself, opening doors to new realms of inquiry and understanding. Faint galaxy clusters, which are groups of galaxies held together by gravity, serve as valuable cosmic touchstones for understanding the universe's history and structure. These clusters are often located far from our own galaxy, making them challenging to observe. However, their faintness is not a drawback. Instead, it allows scientists to delve deeper into the mysteries of dark matter, dark energy, and the evolution of cosmic structures. When astronomers look at these distant clusters, they engage in a kind of cosmic archaeology. The light we see from them today actually left those clusters billions of years ago, providing a glimpse into the universe's past. By studying their composition and how they are distributed across the cosmos, scientists can gather data about the distribution of matter in the universe. This information helps paint a clearer picture of dark matter, which, while invisible, makes up a significant portion of the universe's mass. Moreover, the way light bends around these clusters reveals essential insights into their mass and gravitational influence through a phenomenon known as gravitational lensing. Imagine using a magnifying glass to focus light on a distant object. Gravitational lensing works similarly, allowing us to observe objects further away than we could ordinarily see. This distortion of light provides clues about the underlying mass and structure of the clusters, and by extension, the distribution of dark matter throughout the universe. Faint galaxy clusters also play a crucial role in understanding the expansion of the universe. The characteristics of these clusters can inform scientists about the influence of dark energy, a mysterious force thought to drive the universe's accelerating expansion. By analyzing the distances and interactions of various clusters, researchers can piece together how dark energy has shaped cosmic evolution over billions of years. While faint galaxy clusters may initially appear insignificant, they are, in reality, woven into the very fabric of cosmic investigation. They guide us toward understanding the strange and elusive elements that govern the universe, bridging gaps in our knowledge from the earliest epochs to the current expansion, and keeping the quest for cosmic understanding ever more profound. Fast radio bursts, often referred to as FRBs, are among the most captivating phenomena in astrophysics today. These brief yet intense flashes of radio waves originate from vast distances, potentially billions of light-years away. Their sudden bursts can last just a few milliseconds, but they unleash more energy than the sun emits in nearly a century. What makes these cosmic signals particularly intriguing is their mysterious nature. Each burst appears to come from deep space, yet we have only detected a small fraction of them. Their origins remain largely unknown, leading scientists to propose a range of intriguing possibilities, from the collapse of massive stars to interactions involving neutron stars, or even the cryptic effects of magnetars, which are exceptionally magnetic neutron stars. The frequency and the way FRBs are scattered give researchers clues about the cosmic environment through which their signals travel. For instance, the dispersion of the radio waves as they move through space can highlight the presence of matter in the universe that we might not be able to see directly. This helps scientists construct a map of cosmic structures that influence how light travels across vast distances. Moreover, the ability to detect these bursts and pinpoint their locations opens up new avenues for understanding the evolution of the universe. By studying their patterns and frequencies, researchers hope to unlock secrets about the conditions in the early universe, the formation of galaxies, and the way cosmic matter interacts. The captivating mystery of FRBs invites scientists to explore deeper into the effervescent dance of celestial bodies, encouraging new discoveries and enhancing our understanding of the cosmos. Cosmic voids are vast regions of space that contain very few galaxies compared to the areas around them. These enormous expanses can be thought of as the empty parts of the universe, often spanning hundreds of millions of light-years. Understanding these voids helps us grasp not only the large-scale structure of the universe, but also hints at the boundaries of our cosmic neighborhood. The existence of cosmic voids suggests a fundamental aspect of the universe's composition. As galaxies clump together under the influence of gravity, they form a web-like structure with dense regions, or filaments, surrounding these voids. This arrangement indicates that space is not uniformly distributed. Rather, it shows a complex tapestry where matter is concentrated and where vast emptiness exists in between. When we discuss universal boundaries, we often touch upon the limits of our observable universe. cosmic voids contribute to this conversation because their presence hints at how matter and energy distribute throughout the cosmos. While we can see only up to a certain point, the edge of the observable universe, voids might extend beyond that boundary into regions we cannot detect. These sparsely populated areas also raise intriguing questions about the universe's topology, the shape and structure of space itself. If we think of the universe as a three-dimensional balloon being inflated, cosmic voids might represent those patches of surface that have been less stretched out. They challenge our understanding of what lies beyond our visible realm, prompting questions about the universe's ultimate fate and whether it extends infinitely or is instead contained in some uncharted manner. Cosmic voids are not just empty space, they embody the variety and complexity of the universe. They illustrate how the idea of boundaries in the universe might be perceived, suggesting that while we know our observable universe has limits, the true nature of the cosmos could lead us to vastly different landscapes we have yet to explore. Cosmologists play a vital role in unraveling the mysteries surrounding the universe's edge, a concept that refers to the farthest regions we can observe and the limits of our understanding. They blend observational science with theoretical frameworks to explore the expansive cosmos. By employing advanced telescopes and instruments, cosmologists capture light from distant galaxies, allowing them to construct a detailed map of the universe. These observations reveal the composition and structure of the universe, including vast cosmic structures like galaxy clusters and the distribution of dark matter. Moreover, cosmologists utilize the principles of general relativity and the laws of physics to formulate models that explain how the universe has evolved since its inception. They analyze phenomena such as cosmic background radiation, a remnant from the birth of the universe, providing insights into its early conditions and subsequent expansion. By exploring how galaxies move and cluster, they can infer the universe's overall geometry and curvature. The quest for understanding the universe's edge also leads to investigating cosmic inflation, a rapid expansion that occurred just after the Big Bang. This theory posits that the universe grew exponentially in size, setting the stage for the structures we see today. Cosmologists work to validate or challenge this theory through meticulous analysis of the cosmic microwave background and high redshift objects, which are galaxies that existed when the universe was much younger. In addition, cosmologists delve into dark energy, a mysterious force believed to be driving the accelerated expansion of the universe. By measuring galaxy distributions and light from supernovae, they attempt to understand how this expansion impacts cosmic structures and what it means for the ultimate fate of the universe. Their ongoing research not only enhances our comprehension of the universe's edges, but also inspires new questions about what lies beyond our current observational limits. Through these contributions, cosmologists are piecing together a comprehensive narrative about the universe, bridging gaps in knowledge and certain mysteries that remain tantalizingly out of reach. Astrophysics and cosmology are two branches of astronomy that, while distinct, are deeply intertwined in the quest to understand the universe. Astrophysics delves into the physical properties and behavior of celestial bodies, studying everything from the life cycles of stars to the nature of black holes. In contrast, cosmology focuses on the universe as a whole, exploring its origins, evolution, structure, and ultimate fate. The intersection of these fields becomes particularly evident when examining the universe's boundaries. Astrophysics provides the tools to analyze specific phenomena that shape our cosmic landscape. For instance, the understanding of the life cycle of stars is crucial in cosmology when considering how elements are forged and distributed throughout the universe. These elements contribute to the formation of galaxies, planets, and eventually life itself. Conversely, cosmological theories offer a broader framework that astrophysics can explore in finer detail. The Big Bang theory, a cornerstone of cosmology, posits that the universe has been expanding since its inception. Astrophysicists utilize this concept to investigate the redshift of distant galaxies, revealing how light from these galaxies shifts toward longer wavelengths as they move away, providing evidence of the universe's expansion. This helps delineate the boundaries of observable versus unobservable universe, leading to questions about how much of the universe lies beyond what we can see and measure. And together, these fields collaborate on fundamental questions about dark matter and dark energy, which significantly influence the universe's expansion and structure. Astrophysical observations of gravitational waves and cosmic microwave background radiation feed cosmological models, refining our understanding of the universe's composition and evolution. While astrophysics gives us insight into the individual components of the cosmos, cosmology provides the overarching narrative, allowing humanity to probe the limits of our universe and ponder what lies beyond. This combined effort enriches our understanding, opening dialogue about the potential for multiple universes, the nature of space-time, and the ultimate fate awaiting all existence. The investigation of the universe's boundaries showcases the importance of approaching these questions from both astrophysical and cosmological perspectives. Technological advances in physics have a profound impact on our understanding of universal limits, the ultimate boundaries that define the behavior of the cosmos. These advances allow scientists to explore phenomena that were once purely theoretical, transforming abstract concepts into areas of exploration and experimentation. For instance, the development of powerful telescopes has revolutionized our capacity to observe distant galaxies, stars, and cosmic events. By capturing light that traveled billions of years to reach us, these instruments offer insights into the very early universe, giving clues about its expansion and the limits of space and time. Similarly, detectors placed in deep underground laboratories enable the observation of rare particles resulting from phenomena predicted by physics, such as dark matter interactions. This adds depth to our understanding of the foundational components of the universe, pushing the boundaries of what we deemed knowable. In particle physics, advancements in collider technology have allowed researchers to smash particles at unprecedented speeds, recreating conditions just after the Big Bang. This helps to probe the fundamental forces and particles that govern the universe, revealing if and where our current models of physics hit a ceiling, whether due to energy limitations or unexplained behaviors. Moreover, improvements in computational technologies empower simulations that model complex physical interactions, visualizing scenarios that are too difficult or impossible to recreate in the lab. These simulations can test theories about black holes, the behavior of time and space, and the limits of known physics under extreme conditions. Every new technological development opens up pathways to challenge existing theories and explore areas we previously thought were off-limits, prompting a continuous re-evaluation of what we know about the universe and its fundamental limits. Each breakthrough serves as a stepping stone, paving the way for deeper inquiries about the very nature of reality. Data analysis from space missions plays a crucial role in deepening our understanding of the universe. When a spacecraft is launched, it collects vast amounts of information about various celestial bodies, cosmic phenomena, and the conditions of space itself. This data can include readings on temperature, light, composition, and even the gravitational effects of objects in space. Through meticulous analysis of this information, scientists are able to draw meaningful insights. For example, observations from missions studying distant planets can reveal their atmospheric conditions, helping us to ascertain whether certain planets might support life. Additionally, data gathered from telescopes observing light from ancient stars provides clues about the formation and evolution of the universe itself. Moreover, space missions often investigate fundamental questions such as the origin of cosmic rays, the presence of dark matter and dark energy, and the behavior of black holes. By analyzing these data sets, researchers can create models and simulations, allowing them to predict how celestial phenomena might behave. This understanding can lead to breakthroughs in physics and astronomy, guiding future explorations and informing our knowledge of fundamental forces. The collaborative effort involved in data analysis also promotes the sharing of knowledge across the scientific community. As different missions might focus on diverse aspects, their combined data enriches our understanding and helps to verify or challenge existing theories. Ultimately, the role of data analysis from space missions goes beyond mere observation. It serves as a powerful tool that transforms raw information into profound discoveries about the cosmos and our place within it. Computer simulations serve as powerful tools that help us visualize and understand the vast and often abstract areas of the universe's outer regions. Think of these simulations as intricate models that mimic real-world physical processes on a smaller, manageable scale. By creating algorithms that replicate the fundamental laws of physics, scientists can explore complex phenomena that would be difficult or impossible to observe directly. In outer space, conditions can vary dramatically, from the dense formations of stars to the elusive patterns of dark matter that are believed to exist in large amounts but cannot be seen directly. Through simulations, researchers can create virtual environments that allow them to experiment with different variables and scenarios. For example, they can adjust the mass of celestial bodies or the rates of expansion of different regions of space to see how these changes affect gravitational interactions and the overall structure of the universe. Moreover, simulations can help illustrate phenomena like galaxy formation and the cosmic web, a structure that resembles a giant, tangled network filled with nodes of galaxies. By visualizing the evolution of such structures over billions of years, scientists gain insight into how galaxies evolve, interact, and cluster together. These simulations also provide a testing ground for theories. If predictions made by a simulation align with observations from telescopes or other instruments, it strengthens our understanding of the universe's workings. Conversely, if they do not match, it prompts scientists to revisit and refine their theories. Ultimately, computer simulations make the abstract realm of the cosmos more tangible. They transform complex astrophysical concepts into engaging visuals that enhance our comprehension of the universe's grand design, revealing intricate relationships and patterns that define our outer space environment. Particle physics plays a crucial role in our understanding of the potential end of the universe, providing insights into the fundamental forces and particles that govern cosmic behavior. To grasp how these tiny building blocks can influence the fate of everything, we must first acknowledge that the universe consists of matter and energy interacting through fundamental forces such as gravity, electromagnetism, and the strong and weak nuclear forces. One significant concept in particle physics is the Higgs boson, often referred to as the particle that gives mass to other particles. The properties of the Higgs field may affect the universe's overall stability. If stability were suddenly disrupted, it could lead to a catastrophic event, the so-called vacuum instability. This hypothetical scenario suggests that a shift in the Higgs field could generate a chain reaction of particle transformations, potentially obliterating the existing universe and replacing it with a different state of reality. Additionally, particle physics provides insight into dark matter and dark energy, the mysterious components believed to make up a large portion of the universe. Dark matter, which interacts with ordinary matter only through gravity, contributes to the structure of galaxies. Meanwhile, dark energy is thought to be responsible for the accelerating expansion of the universe. If the balance and interactions between these forces shift, they could lead to various fates, ranging from a slow cooling as the universe expands indefinitely to a potential big crunch, where gravitational forces could eventually draw everything back together. Theoretical scenarios like the heat death of the universe imply that as energy becomes more evenly distributed across space, stars will burn out, galaxies will drift apart, and all forms of life will cease to exist in an increasingly cold and empty cosmos. Each of these outcomes, whether related to vacuum instability, dark energy, or the eventual depletion of usable energy, stems from the underlying principles elucidated by particle physics. By studying the smallest particles, we gain valuable perspective on both the cosmos' evolution and its ultimate fate, revealing that the path toward the end is as complex as the universe itself. Interdisciplinary research plays a crucial role in enhancing our understanding of the expansive boundaries of the universe. By drawing insights from various fields, including physics, astronomy, mathematics, biology, and even philosophy, scientists can approach questions from multiple angles, unlocking new perspectives that a single discipline might overlook. For instance, astrophysicists study celestial phenomena, but when they collaborate with mathematicians skilled in complex algorithms, they can create more sophisticated models that simulate the behavior of galaxies or black holes on a cosmic scale. Biologists, on the other hand, may offer insight into the potential for life in extreme conditions, sparking discussions on what forms life might take in environments on distant planets or moons. This fusion of knowledge encourages innovative thinking. Take the exploration of dark matter and dark energy, for example. While physicists propose theories to explain these enigmatic components of the universe, insights from cosmology and particle physics help ground these concepts in observable data, leading to more robust hypotheses about the universe's structure and fate. Moreover, interdisciplinary approaches can challenge existing paradigms. Philosophers provide critical reflections that can reshape how scientists frame their questions, ensuring that they explore the fundamental assumptions guiding their work. This synergy cultivates a more holistic understanding of universal phenomena and drives forward not only theoretical advancements, but also technological innovations that facilitate further exploration. By merging expertise across disciplines, we not only deepen our knowledge of the universe, but also expand the very limits of what we can comprehend, ultimately bringing us closer to answering some of humanity's most profound questions about existence and the cosmos at large. Scientific debates play a crucial role in advancing our understanding of the universe's edge, a place teeming with mysteries and profound questions. These discussions often bring together researchers with diverse perspectives and expertise, challenging established ideas and encouraging fresh thinking. When scientists engage in debate, they question assumptions, design innovative experiments, and develop new theories. This interactive process resembles a collaborative puzzle-solving effort, where each participant contributes pieces of knowledge and insights, leading to a fuller understanding of complex phenomena. Consider theories about that elusive boundary of the universe, such as dark matter and dark energy. Scientists disagree about their nature and role, prompting rigorous examination and new hypotheses. It is through this healthy contention that better models emerge, which can then be tested and refined. Debates also pave the way for innovation in technology and methods, enabling researchers to gather data previously thought unreachable. As in all scientific endeavors, the dialogue not only sharpens individual ideas, but also propels the entire field forward. Moreover, when debates capture public attention, they engage a broader audience in the scientific process. This interaction can lead to increased funding, more research opportunities, and heightened interest in science education, all of which can accelerate discoveries at the universe's edge. Through constructive argument and collaboration, scientific debates cultivate a fertile ground for breakthrough insights, illuminating the cosmos and expanding our understanding of what lies beyond our current knowledge. When scientists share data across different disciplines, they unlock a treasure trove of insights that can lead to unexpected discoveries and advancements. Each field of study, whether it's biology, physics, or astronomy, operates with its own set of principles and methods. By making data accessible across these boundaries, scientists can see their work through new lenses, revealing patterns and connections that might otherwise remain hidden. One significant lesson learned is the power of collaboration. Diverse perspectives can foster creativity as researchers combine their unique knowledge to solve complex problems. For instance, understanding climate change can benefit from the fields of ecology, geology, and atmospheric sciences all working together. By sharing data, they can create comprehensive models that account for various environmental factors, leading to more effective solutions. Moreover, interdisciplinary data sharing often highlights new questions and challenges. Scientists may encounter unforeseen variables or phenomena that require them to broaden their research scope. This can lead to the formulation of innovative hypotheses. For example, insights from genetic research might inform medical practices, while findings in neuroscience could influence developments in artificial intelligence. Importantly, the practice of sharing data encourages transparency and reproducibility in research. When studies are made open and available to others, it promotes a culture of trust and accountability, which is vital for scientific integrity. Other researchers can test and verify findings, reinforcing the cumulative nature of knowledge. Ultimately, by embracing interdisciplinary data sharing, scientists learn not only about the subjects of their own research, but also gain valuable insights into the interconnectedness of various scientific realms. This collaborative spirit drives progress and enriches our collective understanding of the universe. Collaboration between astronomers and physicists plays a pivotal role in redefining our understanding of the universe. These two disciplines, while distinct, overlap significantly in their inquiries about the cosmos. Astronomers observe celestial phenomena, gathering data on everything from the structure of galaxies to the behavior of distant stars. Meanwhile, physicists strive to understand the underlying principles and forces that govern these phenomena through theoretical frameworks and models. When these professionals join forces, they bring together observational data and theoretical insights to create a more comprehensive picture. For example, physicists develop theories about fundamental forces and particles, while astronomers validate or challenge these theories by collecting data from telescopes and other instruments. If astronomers discover an unexpected pattern in the motion of planets or the expansion of the universe, physicists may be prompted to rethink established theories of gravity or the fabric of spacetime. This dynamic relationship has led to groundbreaking advancements. Take the discovery of gravitational waves, for instance. Astronomers observed these ripples in spacetime generated by massive cosmic events, while physicists had previously predicted their existence through the theory of general relativity. Their collaborative efforts not only confirmed a significant prediction, but also opened up a new avenue for observing the universe, enabling us to detect phenomena that were hitherto invisible. Furthermore, interdisciplinary collaboration often inspires new questions and avenues of research. The mysteries of dark matter and dark energy exemplify this phenomenon. Astronomers observe the effects of these unseen components of the universe through their influence on galaxies and cosmic structures, leading physicists to explore models that might explain their nature. This interplay stimulates innovative theories, suggesting that our understanding of the universe is not static, but rather evolves continuously through shared insights. The partnership between astronomers and physicists fosters a richer dialogue about the universe, allowing for a more nuanced understanding and catalyzing scientific breakthroughs. This synergy exemplifies how the pursuit of knowledge thrives when diverse perspectives converge, ultimately enriching our grasp of the cosmos and our place within it. As we look to the future, several pioneering missions and technologies are gearing up to push the boundaries of our exploration of the universe. One of the most anticipated missions is the James Webb Space Telescope, which promises to enhance our understanding of the cosmos by peering deeper into space and time than ever before. With its powerful instruments, it will examine the formation of stars and galaxies, scrutinize distant exoplanets, and potentially uncover the building blocks of life in other parts of the universe. In addition to this, the European Space Agency is planning the Euclid mission, aimed specifically at understanding dark energy and dark matter, mysteries that make up a large portion of our universe but remain elusive. By mapping billions of galaxies, Euclid seeks to shed light on how these mysterious forces shape the universe's structure and its expansion. Furthermore, human exploration hopes to take a significant leap forward with the Artemis program, which aims to return astronauts to the Moon. This endeavor will not only foster a sustained presence on our lunar surface, but also serve as a proving ground for technologies intended for future missions to Mars. This includes advancements in life support, habitat construction, and sustainable resource utilization, which are critical for long-duration missions to more distant destinations. On a more experimental front, numerous robotic missions are in the pipeline to explore the outer planets and their moons. Missions like NASA's Europa Clipper will conduct detailed reconnaissance of Europa, one of Jupiter's moons, which is believed to have a subsurface ocean that could harbor conditions suitable for life. Additionally, innovative technologies such as space-based laser propulsion could revolutionize how we travel to other celestial bodies. By using powerful beams of light to propel spacecraft, we might achieve higher speeds and more efficient travel than traditional rocket engines allow, enabling missions that stretch even farther into the solar system and beyond. Together, these endeavors not only represent the next steps in our quest to understand the universe, but also highlight our enduring curiosity and determination to explore the final frontier. As we advance, each mission brings us closer to answering profound questions about our existence and the nature of the cosmos. The next generation of telescopes represents a significant leap forward in our quest to understand the universe and its boundaries. These advanced instruments will utilize cutting-edge technologies, enabling us to gather light from the faintest objects in the cosmos. Imagine looking at the night sky and peering not just into the visible spectrum of light, but also understanding the deeper, hidden messages within infrared and ultraviolet light. This expanded vision allows astronomers to study celestial bodies that are typically obscured or too distant to see with current telescopes. One of the most exciting aspects of these new telescopes is their ability to analyze exoplanets, which are planets outside our solar system. With sophisticated imaging and spectroscopic techniques, we will be able to detect and characterize the atmospheres of these distant worlds. This groundbreaking capability could provide crucial insights into the potential for life beyond Earth and reveal the conditions present in environments that lie light years away. Furthermore, the next generation of telescopes will operate in larger arrays, capturing images that are far more detailed than their predecessors. This enhanced resolution means we can observe galaxies that formed soon after the Big Bang. By studying these ancient galaxies, we can piece together how the universe evolved over billions of years. The light from these distant objects carries information about their formation and the laws of physics that governed their development. As we extend our observational reach, the new telescopes will also help us map dark matter and dark energy, two of the most elusive components of our universe. These mysterious forces shape the structure of everything we see and feel, yet their properties remain largely unknown. By observing their effects on surrounding galaxies, we can uncover clues about the universe's expansion and its ultimate fate. Ultimately, the next generation of telescopes will not only deepen our understanding of cosmic boundaries, such as the limits of the observable universe, but will also enhance our grasp of fundamental questions about matter, energy, and our place in the cosmos. With these powerful eyes focused on the sky, we stand on the brink of discoveries that could reshape our understanding of everything we thought we knew about the universe. Quantum computation holds the potential to revolutionize our understanding of the universe in several remarkable ways. At its core, quantum computing exploits the principles of quantum mechanics, allowing it to handle complex calculations much more efficiently than traditional computers. This capability is crucial for the field of astrophysics, where many phenomena involve intricate interactions and vast amounts of data. One significant advancement could be in the area of simulating quantum systems. Current models of particles and their interactions often require approximations, resulting in less accurate representations of reality. Quantum computers can model these systems directly, leading to an unprecedented understanding of fundamental forces and particles. By accurately simulating conditions like those found in the early universe or within black holes, scientists can test theories of physics more rigorously. Furthermore, the analysis of massive datasets generated by telescopes and detectors could be dramatically improved. In areas such as dark matter and dark energy research, where vast amounts of observational data need to be analyzed, quantum algorithms could enhance pattern recognition and anomaly detection. This might help uncover hidden signals or correlations that classical computers struggle to discern. Additionally, quantum communication offers the promise of secure data transfer between distant observatories, ensuring that valuable research findings can be shared without the risk of interception. These secure connections could facilitate global collaborations, bringing together the brightest minds to challenge our understanding of cosmic phenomena. Lastly, advancements in quantum algorithms might enable us to explore complex problems in gravitational physics and cosmology faster than ever before. With the ability to handle higher dimensions and intricate mathematical structures inherent in the universe, quantum computers could help tackle questions about the nature of space-time itself, exploring theories that could unify the various forces of nature. Overall, as quantum computation continues to evolve, it could redefine how we approach the mysteries of the universe, unlocking insights that remain elusive even to our most advanced classical methods. Artificial intelligence and machine learning are revolutionizing cosmic research by enhancing our ability to analyze vast amounts of data generated by telescopes and space missions. In the realm of astronomy, these technologies act like powerful assistants, sifting through millions of images and datasets far more quickly than any human could. By recognizing patterns and anomalies within the data, AI can identify celestial objects ranging from distant galaxies to even the faintest signs of potentially habitable exoplanets. One of the most exciting applications is in the search for gravitational waves. These ripples in spacetime are incredibly subtle and require the analysis of minute changes in data signals. Machine learning algorithms can rapidly process these signals, filtering out noise and highlighting significant events that may indicate a collision of black holes or neutron stars. Moreover, artificial intelligence facilitates the classification of various types of astronomical phenomena. For instance, in identifying and categorizing supernovae or different types of stars, machine learning models can learn from existing data and continually improve in accuracy. This evolution is crucial as the universe is constantly revealing new kinds of celestial events, and these models can adapt quickly to shifting paradigms. In the quest for dark matter and dark energy, AI aids researchers by modeling complex cosmic structures and their dynamics over vast scales of time and space. By simulating how galaxies might interact under different conditions, scientists can better understand the mysterious forces that govern the universe. Importantly, AI's capabilities are not limited to analysis alone. They also enhance predictive modeling, allowing scientists to forecast cosmic events or the likelihood of discovering new celestial bodies based on existing knowledge. This predictive power can guide future observations and experiments, optimizing the use of resources in the search for new discoveries. In short, the fusion of artificial intelligence and machine learning with cosmic research not only accelerates discoveries, but also offers deeper insights into the fundamental workings of our universe, transforming the way scientists explore the cosmos. Private sector space exploration has the potential to revolutionize how we pursue universal discoveries. Traditionally, space exploration has been primarily the domain of government-funded agencies. However, as private companies enter the arena, they bring unique capabilities, innovative practices, and agile approaches that can accelerate discoveries on many fronts. One significant role of private industry is increased funding and investment in research and technology. Private companies often have the resources to invest in advanced technologies, which can lead to breakthroughs that government programs may not prioritize due to budget constraints. This financial support can foster the development of new spacecraft, propulsion systems, and scientific instruments that enhance our ability to explore. Additionally, the private sector can operate with greater flexibility, enabling rapid prototyping and deployment of missions. Unlike government programs, which can be bogged down by bureaucratic processes, private companies can adapt quickly to changing scientific priorities or emerging opportunities in space. This agility allows for timely responses to new discoveries or challenges, facilitating more dynamic exploration efforts. Moreover, private companies are engaging in partnerships with governmental agencies, leveraging their expertise while sharing the risks involved in ambitious space missions. These collaborations often lead to enhanced data collection, analysis, and sharing, promoting a culture of discovery where the findings can benefit everyone. The commercialization of space travel also opens doors for a broader segment of society to participate in exploration efforts. This increased public engagement can lead to more diverse ideas and approaches, fostering innovation. When more voices contribute to the conversation, the potential for groundbreaking discoveries amplifies. Lastly, the role of private sector exploration isn't limited to near-Earth activities. Companies are making strides toward missions aimed at Mars and beyond, as well as the mining of asteroids. These ambitious projects could yield new materials and insights into our solar system's evolution, shaping our understanding of the universe. Private sector space exploration complements and enhances existing scientific efforts, introducing fresh perspectives, technologies, and collaborations. This synergy not only accelerates discovery, but also broadens the horizons of human knowledge in the grand tapestry of the cosmos. The search for extraterrestrial life is fundamentally intertwined with our understanding of the universe's edge. At its core, this quest seeks to answer a profound question. Are we alone in the cosmos? As we explore the vastness of space, scientists look beyond the familiar realms of our own solar system, venturing to the farthest reaches of the observable universe. One of the crucial elements in this search is the study of exoplanets, worlds orbiting stars beyond our Sun. These distant planets vary widely in size, composition, and distance from their stars, prompting researchers to ask whether any of these worlds might harbor conditions conducive to life. The edge of the universe becomes significant in this context, as new astronomical technologies allow us to observe galaxies far away, previously thought beyond our reach. These observations help us to identify potential habitable zones where conditions like temperature and the presence of liquid water might resemble those on Earth. Additionally, our understanding of how life could arise has expanded in light of discoveries made at the cosmic frontier. For instance, extremophiles, organisms that thrive in Earth's most extreme environments, broadcast the message that life can exist in a variety of conditions once deemed inhospitable. This broadens our search, allowing scientists to contemplate a wider array of potential extraterrestrial environments, perhaps even in regions that lie near the universe's edge, such as icy moons orbiting gas giants or the atmospheres of distant, gas-rich planets. The concept of cosmic evolution also plays a role here. As we study the origins and development of galaxies at the edge of the universe, we gain insights into the likelihood of life as a byproduct of stellar and planetary formation processes. The existence of stars generates the conditions necessary for complex chemical reactions, leading to the formation of organic molecules essential for life. By grasping how these processes unfold across the universe's expansive timeline, we start to piece together where and how life might emerge. Finally, the search for extraterrestrial intelligence intersects with the study of the universe's boundaries as researchers deploy advanced technologies, such as powerful telescopes, to listen for signals from potential civilizations. These endeavors reflect our yearning to connect with those who might inhabit the universe's farthest reaches, reminding us that our journey is not merely one of scientific inquiry, but also of existential exploration. As we push the frontiers of space exploration, the insights we gather from studying the universe's edge profoundly impact our quest for alien life, fostering a richer understanding of both the cosmos and our place within it. As scientists seek to unravel the mysteries of the universe, they are constantly exploring phenomena that lie beyond our current observational capabilities. One of the most promising leads is the study of gravitational waves. These ripples in space-time created by massive cosmic events like the merging of black holes or neutron stars offer a novel way to observe the universe. When detected, they reveal details about the events that generate them, allowing us to glimpse phenomena that are otherwise hidden from traditional telescopes. Additionally, researchers are delving into the possibilities presented by dark matter and dark energy, which together constitute a substantial portion of the universe. Although they remain elusive and undetected directly, scientists are employing advanced experiments and observational techniques to infer their properties. Projects like the Large Hadron Collider aim to unlock the secrets of dark matter particles, while expansive sky surveys work to understand the influence of dark energy on the universe's expansion. Another frontier rests in the realm of high-energy astrophysics. Observations through powerful instruments, such as space-based observatories that capture X-rays and gamma rays, allow us to observe extreme cosmic phenomena. These include powerful gamma-ray bursts or enigmatic neutron stars, providing crucial insights into the fundamental processes governing the universe. The pursuit of exoplanets also holds great promise. Using techniques like transit measurements or direct imaging, astronomers are uncovering distant worlds that may harbor conditions suitable for life. The data gathered may lead to discoveries far beyond our solar system, expanding our understanding of planetary systems. Lastly, advancements in technology continue to push the limits of our observational capacities. Next-generation telescopes and satellite missions are set to enhance our view of the cosmos significantly. As these tools become operational, they may uncover phenomena that have thus far remained beyond our reach, reshaping our understanding of the universe in the process. Collectively, these avenues are paving the way for groundbreaking discoveries that may ultimately redefine our grasp of what lies beyond the known. Breakthroughs in propulsion technology could revolutionize our exploration of the universe and deepen our understanding of its mysteries. Imagine traveling to distant stars or even other galaxies within a human lifetime instead of the countless generations it would normally take. With advanced propulsion systems, we could reach areas of the cosmos that were previously deemed unreachable, allowing us to gather data from places we've only dreamed of visiting. One of the most exciting possibilities is the use of concepts like ion propulsion or even theoretical methods like nuclear thermal propulsion. These technologies operate on the principle of producing thrust by expelling particles at high velocity, which could allow for more efficient travel over vast distances than traditional chemical rockets. As these systems become more efficient, our spacecraft could carry heavier instruments for scientific exploration, potentially leading to groundbreaking discoveries about celestial bodies, cosmic phenomena, and the origins of the universe itself. Moreover, enhanced propulsion technology would facilitate the search for extraterrestrial life. Increased mobility could enable missions to moons and planets within our solar system that have suitable conditions for life, such as Europa or Mars. If we can traverse to these locations more rapidly and effectively, our ability to gather samples and conduct experiments would dramatically improve. Additionally, understanding the physics behind advanced propulsion could lead to new insights into fundamental laws governing the universe. For instance, investigating warp drives or concepts that allow for faster-than-light travel challenges our current understanding of space and time. It could also reveal new aspects of relativity and quantum mechanics, expanding our grasp of fundamental scientific principles. Advancements in propulsion technology would not just enhance our ability to explore the far reaches of the universe, they would also transform our theoretical frameworks, pushing the boundaries of what we know and reshaping our place in the cosmos. Through these developments, we would not only gaze into the stars, but we might also unlock the secrets they hold. Scientists envision a future where international collaborations on exploring the universe become increasingly vital. With the vastness of space and the complexity of the challenges it presents, no single nation has the resources or expertise to venture far beyond our planet alone. Imagine a global network of space agencies, researchers, and private organizations pooling their knowledge and technology to tackle ambitious missions together. This cooperative effort could lead to joint missions to Mars, where scientists from various countries might share their capabilities in developing landing technologies, rover designs, and sustainable life support systems. Such collaborations would not only enhance the scientific yield of each mission, but also foster peaceful relations and shared goals among nations. We may also see partnerships in astronomical observation. Various countries could deploy observatories worldwide, working together to monitor celestial events and gather data on phenomena like supernova and exoplanets. This united approach would ensure that the best minds from diverse backgrounds work together to answer fundamental questions about our universe, from the nature of dark matter to the potential for life elsewhere. These international collaborations could extend to tackling the logistics of human settlement on other planets or even asteroids. By combining resources, nations could develop the technologies needed for sustainable living and resource utilization off Earth. Over time, we might witness a new era of exploration where humanity collectively paves the way for future generations to journey beyond, sharing not only the risks but also the wonders of the cosmos together. Educational outreach serves as a powerful catalyst in inspiring young minds to explore the universe. It opens the doors to the wonders of space through engaging activities, interactive lessons, and real-world applications. By introducing children and teenagers to concepts such as the vastness of the cosmos, the intricate workings of celestial bodies, and the challenges of space exploration, we plant the seeds of curiosity and wonder. Programs that involve hands-on experiences, like building scale models of planets or simulating rocket launches, not only make learning enjoyable, but also reinforce scientific principles. When students see a model rocket soar into the sky or watch a simulation of a rover navigating the Martian surface, they connect abstract concepts to tangible realities. This experiential learning fosters enthusiasm and motivates them to think critically about science and technology. Moreover, storytelling plays an essential role in outreach. Narratives about pioneering astronauts, groundbreaking scientists, and thrilling discoveries capture the imagination. Personal stories of overcoming obstacles in the pursuit of knowledge resonate deeply, encouraging young people to envision themselves as future innovators and explorers. Incorporating diverse voices in these narratives further allows students from all backgrounds to see themselves reflected in the journey of space exploration. Access to mentors and role models also cannot be overstated. Initiatives that connect students with scientists and engineers provide invaluable insights. These mentors not only share knowledge but also inspire confidence, demonstrating that anyone can contribute to the field of space. Ultimately, effective educational outreach cultivates an environment where curiosity thrives. By igniting passion for science, technology, engineering, and mathematics, and by fostering a community of support, we empower the next generation to pursue their interest in the cosmos, making them the explorers and innovators of tomorrow. The universe is vast and full of mysteries, and with the right encouragement, today's youth will be tomorrow's pioneers, uncovering secrets yet to be discovered. Exploring the universe's edges captivates and transforms human culture in profound ways. The quest to understand what lies beyond our familiar surroundings ignites imagination and inspires creativity across various fields. When we peer into the depths of space, we are not just observing distant galaxies or cosmic phenomena, we are reflecting on our place in the cosmos. Questions about our origins and destiny challenge us to rethink our values, philosophies, and even our relationships with one another. The discoveries made at the universe's fringes often resonate deeply within humanity. The sight of distant stars and galaxies sparks stories of exploration, wonder, and the eternal search for knowledge. Artists, writers, and filmmakers draw upon these cosmic themes, crafting narratives that touch on existential questions and the possibilities of life beyond Earth. Science fiction, in particular, flourishes in this rich, fertile ground, encouraging audiences to envision future technologies and societies shaped by interstellar travel. Additionally, the visual splendors revealed through telescopes and space missions foster a shared sense of human achievement. Images of stunning nebulae and the vast expanse of our universe remind us of our collective journey as a species. This can foster a sense of unity and responsibility, urging us to collaborate in the stewardship of our planet while reaching for the stars. As researchers push the boundaries of our understanding, an increasingly diverse group of individuals becomes inspired to engage with science and technology. This curiosity nurtures a culture that values inquiry, innovation, and critical thinking. The pursuit of answers at the universe's edges can transform education, encouraging young minds to explore fields in science, engineering, and the arts, propelling society forward. Our exploration of the universe's edges serves not just as a scientific endeavor, but as a catalyst for cultural transformation, fostering a sense of wonder and connectedness that echoes through art, thought, and our shared human experience. The exploration of the universe's boundaries stirs profound philosophical questions that transcend mere scientific inquiry. First, we ponder the very essence of existence. When we think about the universe's edges, we are essentially asking what lies beyond those limits and whether anything exists at all. This invites a deeper reflection on the nature of reality itself. Are the universe and everything within it the only physical attributes of existence? Or is there something greater, perhaps an infinite realm beyond our comprehension? Another thought-provoking question centers around the concept of time and space. If the universe has boundaries, what does that mean for our understanding of time? Are we to consider that time itself may also have a beginning and an end, shaping how we perceive our own existence within this vast expanse? This leads us to consider the implications of cosmic origin. What sparked the universe into being, and what does that imply about the nature of cause and effect? Furthermore, the examination of boundaries invokes inquiries into human significance and our place in the cosmos. Are we mere specks of dust in an enormous void, or is our consciousness and capacity for thought an integral part of a grander scheme? This question challenges us to reflect on the purpose of life. If the universe is boundless, do we hold greater relevance in understanding its mysteries, or do we simply exist within a system that is indifferent to our presence? Lastly, the inquiry into the universe's structure may provoke ethical considerations. As we search for answers about our cosmic home, how should we conduct ourselves in relation to the universe and each other? Are there moral implications for our actions on Earth and beyond, especially as we consider the possibility of life elsewhere in the cosmos? These philosophical reflections, ignited by the study of the universe's limits, compel us to investigate not just the stars, but also our own humanity. Understanding the universe's limits profoundly shapes our perspective of Earth and our place within the cosmos. When we explore the boundaries of the universe, its vastness, its age, and the fundamental laws governing its behavior, we begin to appreciate the intricate balance and fragility of our own planet. Earth is not just a habitat, it's an oasis of life in an overwhelmingly expansive and largely inhospitable universe. As we learn that the universe stretches beyond what we can see, extending to infinite distances, we realize that Earth occupies a tiny fraction of this grand landscape. This knowledge helps us recognize the uniqueness of our home, fostering a sense of awe for the delicate conditions that allow life to thrive here. Earth's atmosphere, the presence of liquid water, and the right temperature range are not trivial. They are exceptional amid the universe's extremes. Moreover, discoveries about cosmic events, such as the life cycle of stars and the occurrence of phenomena like supernovae, draw attention to the interconnectedness of everything in the universe. We are reminded that the very elements that make up our bodies were forged in the hearts of stars, connecting us to the cosmic processes far beyond our planet. This perspective can temper human conflict, as it emphasizes our shared existence and collective responsibility towards each other and our environment. Additionally, understanding the limits of the universe also raises critical questions about sustainability and urgency regarding our resource use. With physical limits in mind, recognizing that Earth's resources are finite prompts a more conscientious approach to living. This knowledge inspires efforts in conservation and innovation, urging humanity to safeguard this beautiful blue planet, pivotal not just for us, but perhaps for life as we understand it in the universe. A deeper understanding of the universe's limits does not diminish our existence, but uplifts it, urging us to act as stewards of Earth while fostering a greater appreciation for the extraordinary conditions that make life possible. Space exploration captivates the human imagination like few other pursuits. It represents the ultimate quest for knowledge, pushing the boundaries of what we understand about ourselves and the universe around us. When we look up at the night sky, we see not just stars, but the potential for discovery and connection with worlds beyond our own. This quest stirs a deep curiosity that has existed throughout human history, prompting us to wonder if we are alone in the cosmos and what mysteries lie beyond our planet. As we send spacecraft to distant planets and probe the depths of space, we transform mere curiosity into tangible achievements. Each mission, whether landing on the Moon, exploring Mars, or capturing images of distant galaxies, fuels a collective narrative that weaves together science, engineering, and the human spirit of adventure. These journeys inspire generations to dream big and reach for the stars, literally and metaphorically. Moreover, the images and discoveries made through space exploration evoke awe and wonder, prompting people to question fundamental aspects of existence such as life, our place in the universe, and the future of humanity. They instigate conversations about technology, cooperation, and the possibility of encountering life elsewhere. Each mission serves as a reminder of our shared aspirations and challenges, creating a sense of unity amid the vastness of the universe. Ultimately, space exploration is not just a scientific endeavor, it's a reflection of human ambition, resilience, and creativity. It enriches our cultural fabric and instills hope for the future, suggesting that beyond our current understanding lies an infinite horizon filled with potential discoveries waiting to be unlocked. Discoveries about the universe's edge could profoundly reshape our understanding of existence and our place within it. At the forefront, these findings may reveal the structure and fate of the universe, shedding light on whether it is finite or infinite. This perspective could alter our philosophical and scientific reflections on life, prompting humanity to reconsider its role in the cosmos. Moreover, if we were to understand the nature of dark energy and the universe's expansion, we could potentially predict the long-term fate of galaxies, stars, and even our solar system. Knowing that the universe might be accelerating away or might eventually contract could shift our focus towards long-term survival strategies and advancements in technology that ensure humanity's continuity, perhaps on other celestial bodies. In addition, discoveries at the universe's edge could provoke a revolutionary shift in our technological pursuits. Understanding extreme cosmic phenomena, such as the behavior of matter under intense gravitational forces or the conditions near black holes, could inspire innovations in fields like energy generation, materials science, and even computing. These advancements might empower humanity to harness energy more efficiently or devise new means of space travel, transforming our capability to explore beyond our immediate cosmic neighborhood. Furthermore, these revelations could unify humanity under a shared purpose. The inspiration drawn from our exploration into the vast unknown could ignite a collective ambition to transcend terrestrial limitations, promoting international collaboration in scientific pursuits. As we learn more about the universe, the interconnectedness of all life may become more apparent, fostering a deeper appreciation for the delicate balance of our home planet in the vast expanse of space. Ultimately, the voyage into understanding the universe's edge could redefine not just technological and scientific ambitions, but also our very identity as a species, knitting together our diverse experiences into a common narrative of exploration, discovery, and a yearning for knowledge that may transcend the stars themselves. Unlocking the secrets of the cosmos can significantly shape the trajectory of scientific endeavors. When we make groundbreaking discoveries about the universe, such as understanding dark matter or revealing the nature of black holes, we spark a renewed sense of curiosity and direction in scientific research. These revelations often highlight new questions that demand attention, leading scientists to prioritize investigations that may have seemed less crucial before. For instance, if we were to understand the origins of the universe better, this might shift focus toward unraveling the fundamental laws of physics that govern it. Researchers could pivot their efforts toward areas like particle physics or high-energy astrophysics, emphasizing experiments that probe deeper into the fabric of reality. Similarly, understanding exoplanets and their atmospheres could prioritize the search for extraterrestrial life, leading to advancements in astrobiology and planetary science. Moreover, cosmic discoveries often lead to technological advancements as the tools developed for space exploration can find applications on Earth. This interplay can inspire funding and resource allocation toward fields such as engineering, data science, and environmental research. The excitement generated by verifying theories or unveiling cosmic phenomena invigorates not just astronomy, but a wide array of scientific disciplines, guiding exploration where human knowledge craves expansion. Ultimately, as we solve cosmic mysteries, we are gifted with a broader perspective of our place in the universe, prompting a re-evaluation of what questions need answering and what technologies and strategies will best serve our quest for knowledge. Each answer nudges us closer to new mysteries, crafting a dynamic landscape of scientific priorities shaped by our evolving understanding of the cosmos. Historical interpretations of the universe's limits have significantly shaped modern inquiries into cosmic phenomena. In ancient times, many civilizations viewed the universe as a fixed, geocentric system where Earth was thought to be the center of everything. This perspective confined humanity's understanding, suggesting that the stars and planets moved in perfect circles around our planet. As observational tools improved and thinkers like Copernicus introduced the heliocentric model, proposing that planets revolve around the sun, the limits of the universe expanded in a conceptual sense. Moving forward to the 20th century, the advent of the telescope revealed that our galaxy, the Milky Way, was just one of countless galaxies, fundamentally altering our perception of the universe's vastness. With the discovery of the expanding universe, initiated by Edwin Hubble, came the idea that the universe was not static but dynamic. This shift prompted inquiries into its origins, leading to the development of the Big Bang theory, which posits that the universe began from a singular, incredibly hot and dense state. Today, these evolving historical insights form the backbone of scientific exploration. Current research into dark matter and dark energy, the mysterious substances that seem to drive the universe's expansion, builds directly on prior models. Limits are now understood not as fixed boundaries, but as concepts that can change, reflecting our ongoing quest for knowledge. Researchers utilize advanced technology, including powerful telescopes and particle accelerators, to probe the universe's edges, attempting to uncover its composition and ultimate fate. Thus, historical interpretations remind us that each breakthrough fosters a deeper appreciation for our cosmic context. They underscore the importance of remaining open to new discoveries that could forever change our understanding of those limits. The pursuit to explore not just the far reaches of space, but also the fundamental laws governing it continues to evolve, driven by lessons learned from the past. Throughout history, humanity's exploration of the cosmos has sparked a rich tapestry of cultural narratives, often reflecting our hopes, fears, and aspirations. The vastness of space, once a realm of myth and wonder, now serves as a backdrop for stories that question our place in the universe. From ancient civilizations that look to the stars to explain their existence, to modern science fiction that explores technological advancement and alien encounters, cosmic boundary explorations have profoundly shaped our storytelling. One prominent narrative is the idea of humanity as explorers. As we developed the technology to venture beyond our planet, stories began to emerge about brave astronauts journeying into the unknown, facing both incredible wonders and terrifying uncertainties. This narrative is epitomized in various films and literature where protagonists grapple with isolation, the fragility of life in space, and the quest for meaning amid the vast, cold cosmos. These themes resonate deeply within us, They evoke our own fears about the unknown and our relentless desire for discovery. Another compelling cultural narrative is the search for extraterrestrial life. This quest has inspired countless stories that ponder the implications of discovering intelligent beings beyond Earth. In these tales, humanity's very nature is questioned. Are we alone in the universe? And if we are not, how will we relate to those who share it? Films and books often depict encounters that challenge our understanding of life, ethics, and civilization. They encourage reflection on our own humanity, prompting us to consider how we would react to the discovery of new forms of life, with all their complexities and the dialogue that such encounters would inspire. The exploration of cosmic boundaries has also influenced philosophical narratives regarding existence and destiny. The vastness of space can provoke profound questions about our role in the universe, sparking debates about fate versus free will. This idea has been explored through various philosophical lenses in literature and film, where characters confront their own limitations and the grand forces that govern existence. These narratives challenge us to think about our destinies in the universe and the legacy we wish to leave behind. As we push the boundaries of space exploration, whether through robotic missions to distant planets or human endeavors to reach Mars, these cultural narratives continue to evolve. They inspire new generations to ponder not just what lies beyond our world, but also what it means to be human in a universe that is still so largely mysterious. Each journey into the cosmic void reshapes our understanding and storytelling, becoming a reflection of our collective consciousness and an exploration of our intertwined fate with the universe. As our scientific understanding of the universe expands, the individual worldviews that shape how we see our place within it evolve considerably. Initially, many people viewed the cosmos through a lens dominated by myths, legends, and religious beliefs, where celestial events were often attributed to the actions of deities. Such perspectives provided comfort, explaining phenomena that were otherwise mysterious, such as the changing seasons or the movement of celestial bodies. As science began to uncover the laws of nature, this narrative shifted. The heliocentric model, which placed the Sun at the center of our solar system, challenged the long-held notion that Earth was the center of the universe. This groundbreaking revelation forced a reconsideration of humanity's position in the cosmos, igniting a more questioning attitude. With subsequent discoveries, like the laws of gravity or the nature of light, people started to recognize that there were rational, scientific explanations for many phenomena. As knowledge deepens further, such as through insights from astronomy, cosmology, and physics, individuals begin to realize that the universe is vast beyond imagination and full of mysteries still waiting to be explored. The notion of life existing elsewhere becomes increasingly plausible. Such realizations can lead to profound shifts in perspective. Rather than feeling isolated on a small planet, many now appreciate being one part of a gigantic, interconnected cosmic tapestry. Moreover, as scientific advancements draw back the curtain on the grand stories of the universe, like the formation of stars, the evolution of galaxies, or the basic principles governing all matter, the overall sense of human significance transforms. With an expanding knowledge of concepts like the Big Bang and the relentless expansion of the universe, individuals grapple with both their insignificance and the remarkable connection they share with what lies beyond. This evolving worldview also influences emotional and philosophical considerations. As scientific literacy spreads, people become more inclined to seek evidence-based answers rather than adhering strictly to tradition or dogma. This shift often fosters a sense of curiosity and a desire to explore, leading to a more inquisitive nature that values exploration and discovery. While some may find this daunting, viewing existence through a scientific framework can also inspire awe and wonder, promoting a deeper appreciation for the intricate workings of the universe and our place within it. As humanity's understanding grows, so too does the complexity and nuance of our worldviews. Each new discovery acts like a piece of a puzzle, allowing individuals to reconstruct their understanding of existence in a way that integrates scientific insight with personal meaning and purpose. The pursuit of universal knowledge fundamentally shapes ethical considerations on Earth, creating a complex interplay between discovery and responsibility. As we explore the vast universe, we are often driven by the desire to understand our origins, the nature of existence, and the potential for life beyond our planet. This quest compels us to question how our newfound insights impact not only our understanding of ourselves, but also the moral principles that guide our interactions with each other and the environment. For instance, advancements in space exploration lead to developments in technology that can benefit humanity, but they can also raise ethical dilemmas. The challenge lies in determining who has access to these transformative technologies. When innovations arise from universal knowledge, ensuring equitable distribution becomes critical, as inequalities can deepen if only a privileged few benefit. Thus, a balance must be struck between the excitement of discovery and the imperative to share these advancements justly. Additionally, as we contemplate the potential for extraterrestrial life or the possibility of colonizing other planets, new ethical questions emerge. For example, if we were to discover microbial life on another planet, it prompts us to consider our responsibilities toward these life forms. Can we prioritize human exploration without jeopardizing other ecosystems? The answers to these questions require a significant ethical framework that respects life in all forms, urging us to act with foresight and care. Moreover, as we uncover universal truths, we must reconcile them with varying cultural beliefs and values on Earth. The quest for understanding can challenge traditional worldviews, leading to ethical conflicts that necessitate dialogue and mutual respect. The knowledge we gain must encourage us to foster collaboration and inclusivity rather than division and conflict. The pursuit of universal knowledge acts as a catalyst for reflection on ethical considerations. It pushes us to navigate our responsibilities not only as explorers of the cosmos, but also as stewards of our planet and its diverse inhabitants. This journey ultimately calls for a commitment to thoughtful engagement with the implications of our discoveries, urging us to envision a future where knowledge serves to uplift all of humanity rather than create a divide. Humans possess a deep-seated curiosity about the unknown, and this intrinsic interest in what lies beyond the known universe stems from our natural desire to explore and understand our surroundings. Ever since our ancestors gazed at the night sky, wondering about the stars, we have sought to unravel the mysteries that lie outside our planet. This quest for knowledge is akin to a fundamental drive. It shapes our culture, fuels scientific inquiry, and inspires innovation. The unknown offers both a sense of wonder and a challenge. For many, the vastness of space symbolizes the ultimate frontier, a realm filled with secrets that could expand our comprehension of existence. The questions we grapple with, such as whether we are alone in the universe or what the very fabric of reality is, push us to seek answers, reminding us of our place in the cosmos. Exploring beyond our world helps us connect with the larger narrative of life itself. Each discovery, whether it be the identification of distant galaxies or the understanding of cosmic phenomena like black holes, enriches our worldview and ignites a sense of shared adventure. As we learn more about the universe, we uncover more about ourselves, our history, and our potential future. It's this intricate interplay of curiosity, discovery, and self-reflection that compels us to gaze into the depths of space, yearning to know what lies just beyond our reach. Scientists navigate the uncertain terrain of the universe's mysteries by employing a multifaceted approach that blends creativity, rigorous experimentation, and collaborative inquiry. They begin by acknowledging the limitations of their current knowledge, understanding that each question often leads to new puzzles rather than definitive answers. This perspective fuels their quest for understanding. One crucial method is the development of hypotheses, educated guesses based on existing theories and observations. These hypotheses guide researchers in designing experiments or observations aimed at gathering more data, whether it be through telescopes probing distant galaxies or particle colliders revealing the hidden secrets of matter. Each experiment becomes a step forward, even if the results are sometimes unexpected or fail to confirm existing theories. Moreover, scientists embrace technological advancement to extend their reach. Innovations such as advanced sensors and computational models allow for the exploration of realms that were previously unimaginable. For instance, the advent of powerful space telescopes has vastly expanded our ability to observe exoplanets and cosmic phenomena, shedding light on areas of the universe that remain cloaked in mystery. Collaboration is another vital component. Scientists from diverse fields come together, fostering interdisciplinary dialogue that enriches their collective understanding. This cooperative spirit cultivates knowledge sharing that can spark breakthroughs, allowing the cross-pollination of ideas that enhance comprehension across various scientific disciplines. Lastly, scientists maintain a sense of open-mindedness and adaptability. They recognize that the universe often behaves in ways that defy initial expectations. The ability to revise theories in light of new evidence is a hallmark of scientific progress. By embracing uncertainty as a crucial element in the pursuit of knowledge, they continue to push the boundaries of what we know about the universe, turning questions into discoveries that inspire future generations. Cosmologists face the exciting challenge of conveying complex ideas about the universe's vastness and its mysterious edge. They utilize various methods to bridge the gap between intricate science and public understanding. One of the primary techniques involves analogies which relate unfamiliar concepts to everyday experiences. By comparing the universe to a balloon that expands or a fabric that stretches, they help illustrate notions of space and time that are difficult to grasp. Visualization is another powerful tool in their arsenal. Through detailed illustrations, computer simulations, and even virtual reality experiences, they create vivid representations of cosmic phenomena. These visuals allow viewers to witness concepts such as the curvature of space or the distribution of galaxies in a way that words alone cannot achieve. Storytelling also plays an essential role. By weaving narratives around the life cycle of stars, the birth of galaxies, or the enigmatic nature of dark matter, cosmologists engage the audience emotionally and intellectually. These stories capture the essence of complex processes in the universe, making them relatable and inspiring curiosity. Additionally, public lectures, documentaries, and educational outreach initiatives serve to inform and engage the general populace. Through these platforms, cosmologists present their findings and theories in a structured manner, inviting questions and discussions that further clarify their ideas. Lastly, collaboration with artists and communicators helps translate technical language into accessible content. This partnership enhances the visual and narrative quality of scientific ideas, making them more appealing and understandable to a broader audience. In sum, through analogies, visualization, storytelling, public engagement, and creative collaboration, cosmologists effectively illuminate the abstract concepts surrounding the universe's edge, inviting all of us to explore the cosmos together. The question of the universe's boundaries is one that both fascinates and challenges scientists. Imagine standing at the very edge of a vast and uncharted ocean where endless possibilities await. This metaphorical edge of the universe propels researchers to ponder not only what exists beyond our observable limits, but also what the very nature of those boundaries might be. The mystery surrounding the universe's edges inspires scientists to think creatively and explore ideas that defy common understanding. For instance, does the universe have a definite shape? Some theorize that it could be infinite, constantly expanding like a balloon being inflated, while others propose it may be curved back upon itself, much like a sphere. Each hypothesis demands innovative thinking and fresh concepts as scientists test their ideas against collected data. Moreover, this enigma often leads to interdisciplinary collaboration, where astrophysicists work alongside mathematicians, computer scientists, and philosophers. This blending of disciplines can yield breakthroughs. The quest to understand dark matter and dark energy, both mysterious components that appear to influence the universe, further illustrates how the unknown encourages diverse approaches and novel experiments. The obscurity of the universe's boundaries serves as a canvas for scientific creativity. It prompts movement beyond established theories, encouraging the exploration of concepts such as alternate dimensions or the multiverse. Each question posed adds layers to our understanding and propels humanity further into the depths of cosmic inquiry, demonstrating that the mysteries of the universe are not just puzzles to solve, but are gateways to endless innovation and discovery. The pursuit of understanding the universe's edge has profoundly shaped the course of scientific discovery throughout history. From ancient philosophers gazing at the stars and speculating about celestial bodies, to modern scientists mapping the cosmos, this quest has driven humanity's desire to comprehend the fundamental nature of existence. In the age of exploration, the boundaries of Earth spurred astronomical advancements. As navigators sought to chart the skies for safer voyages, they developed instruments like the telescope, ultimately leading to groundbreaking observations by figures such as Galileo. His studies unveiled moons orbiting Jupiter, challenging the long-held belief that all celestial bodies revolved around the Earth. This pivotal moment moved humanity from an Earth-centric universe to a broader perspective, laying groundwork for a heliocentric model. As notions of the universe expanded, the concept of infinity also began to emerge. The realization that the night sky holds countless stars, many far beyond our immediate reach, inspired thinkers like Isaac Newton. He formulated laws of motion and universal gravitation that not only explained phenomena on Earth, but also offered insights into celestial mechanics. Newton's work set the stage for further exploration of the cosmos, revealing that the universe followed discernible laws, guiding future generations of astronomers and physicists. In the 20th century, the quest took another leap forward with the advent of powerful telescopes capable of perceiving distant galaxies. This era brought forth the idea that the universe is not static, but rather expanding. Edwin Hubble's observations taught us that galaxies are moving away from each other, suggesting that the universe itself is growing. This expansion led to the formulation of the Big Bang theory, positing that it all began from an incredibly dense state, radically reshaping our understanding of cosmic origins and time. Moreover, the quest has consistently intersected with technological advancements. Each leap in our understanding of the universe often coincided with improvements in measurement and observation tools, from radio telescopes detecting cosmic radiation to space probes venturing into the farthest reaches of our solar system. Such innovations are directly influenced by our desire to grasp what lies beyond our sight, demonstrating the interplay between theoretical inquiry and practical application. Ultimately, the journey to explore the universe's edge reveals our deep-seated curiosity and relentless pursuit of knowledge. Each scientific breakthrough is a stepping stone, revealing not only the mysteries of the cosmos, but also our place within it. As scientists continue to seek answers about what lies beyond the observable universe, this quest remains a vital thread woven into the fabric of human understanding. The pursuit of understanding the universe shapes our psychological landscape in profound ways. Humanity's innate curiosity drives us to explore the cosmos, leading to a sense of wonder and awe. This expansive curiosity encourages creativity and innovation, fostering a spirit of exploration that is fundamental to our nature. As we uncover the mysteries of space, whether through the discovery of distant galaxies or the study of cosmic phenomena, we experience a mix of fascination and humility. The vastness of the cosmos often puts our lives and problems into perspective, highlighting both our insignificance and our unique place within this grand tapestry of existence. This duality can evoke feelings of connectedness to the universe, promoting a deeper appreciation for life and the natural world. However, the quest to understand the universe can also provoke existential questions. As we ponder our origins and our place in the cosmos, it may lead some to experience anxiety or uncertainty about the future. Concepts like the possibility of extraterrestrial life, the fate of our planet, or the end of the universe itself can elicit a range of emotions, from fear to hope. Additionally, the technical and expansive nature of space research can foster a sense of community and belonging among those who share in this quest. Collaborations between scientists, enthusiasts, and everyday people create bonds based on shared exploration. This communal experience can offer a sense of purpose as individuals contribute to a collective understanding that transcends geographic and cultural boundaries. Ultimately, the psychological impacts of humanity's quest to comprehend the universe are multifaceted. It ignites the imagination, challenges the mind, and encourages profound reflection on our existence. In the face of these cosmic mysteries, we are compelled to confront not just the stars, but also the depths of our own human experience. Artists and writers play a vital role in deepening our understanding of the universe's mysteries by translating complex scientific concepts into relatable narratives and visuals. They take the abstract and often daunting ideas of physics, astronomy, and cosmology and render them accessible to the wider public. For instance, when an author imagines a journey through space or the experience of life on another planet, they not only spark our imagination, but also encourage curiosity about real scientific principles. Visual art can convey the magnificence of the cosmos in a visceral way. Stunning images of galaxies, nebulae, and celestial phenomena invite viewers to contemplate their existence and significance outside of cold scientific parameters. These images may evoke emotional responses that lead to a deeper connection with the cosmos, inspiring individuals to explore questions of existence and our place within this vast universe. Moreover, stories that weave in scientific themes often present philosophical questions about humanity, the nature of reality, or the ethical implications of exploring new worlds. By doing so, artists and writers encourage an ongoing dialogue about our collective human experience and aspirations, driving society to think critically about advancements in science and technology. This fusion of art and science ultimately broadens our comprehension of the universe, making its mysteries more approachable and igniting the spark of wonder in all of us. Throughout history, humans have looked up at the night sky and sought to understand the mysteries of the universe. Myths and legends from ancient cultures often illustrated celestial phenomena in ways that reflected their environment, beliefs, and aspirations. For instance, many civilizations created stories about star constellations, attributing significant characters and events to their shapes, such as heroes, animals, or deities. These narratives offered explanations for the seemingly chaotic cosmos and provided a framework for understanding natural events such as seasons or eclipses. Interestingly, modern discoveries in astronomy resonate with many themes found in these ancient tales. For example, consider the myth of the celestial sea, often represented by the Milky Way. Ancient peoples would associate this luminous band across the night sky with rivers or pathways, symbolizing a journey to the afterlife. Today's scientists describe the Milky Way as a vast spiral galaxy filled with billions of stars, each potentially hosting its own planets, hinting at the possibility of life beyond Earth. This aligns with the mythical theme of exploration and the pursuit of immortality through knowledge. Similarly, the idea of creation stories, often steeped in dramatic events such as cosmic battles or the emergence of the universe from chaos, parallels our contemporary understanding of the Big Bang theory. Just as many cultures depicted the universe as born from an immense explosion or a primordial conflict, modern astrophysics explains that the cosmos began from a single, incredibly dense point and has been expanding ever since. This fundamental transformation echoes the tumultuous narratives told by our ancestors, turning chaos into order. Moreover, thought-provoking correlations arise in the legends about cosmic beings or giants that shape the world. Many mythical figures represent forces of nature, embodying power, creation, or destruction. Today, researchers study cosmic events like supernovae or black holes, which possess the potential to reshape entire galaxies and influence the formation of new stars and planets. The connection between the mythological giants and the immense natural forces we now understand illustrates humanity's long-standing fascination with the powerful and sometimes unfathomable processes of the universe. The rich tapestry of historical myths illustrates humanity's quest to comprehend our place in the cosmos. As we uncover deeper scientific truths, it becomes evident that these timeless stories still resonate, bridging our ancient understandings with contemporary insights. The universe remains a vast realm of wonder, captivating both the imaginative hearts of our ancestors and the inquisitive minds of today's explorers. Exploring the universe's edge invites us to confront profound existential questions about our existence and the nature of reality. Picture standing at the boundary of the known cosmos, where the vastness stretches infinitely. This perspective encourages reflections on our place within this immense expanse. What does it mean to be a part of something so grand and largely unexplored? As scientists investigate the universe's edge, they grapple with notions of beginnings and ends. How did the universe come into being? Is there truly a boundary to the cosmos, or is it a continuous entity that defies our understanding? These inquiries tap into our fundamental desire to comprehend the origins of existence itself. The sheer scale of the universe and the mystery enveloping its edges prompt us to think about our significance in an almost unfathomable setting. Moreover, contemplating the universe's limits raises questions about time. If the universe has an edge, what lies beyond it? Is there a reality that exists outside our perception? This intersection of time and space challenges our understanding of eternity and our fleeting moments within it. The idea of an expanding universe also evokes philosophical reflections. As galaxies drift apart, we must face the implications of isolation and connection. What is our future in an ever-expanding cosmos? Will we lose our celestial neighborhood to the void? These thoughts instill a sense of urgency regarding our actions, individually and collectively, on Earth. By studying the universe's edge, we are not merely tracking stars and galaxies. We are engaging with the essential questions of purpose, existence, and what it means to be human in a universe that is both magnificent and tragically indifferent. Each discovery not only broadens our scientific horizons, but also deepens our understanding of ourselves and our place in the grand tapestry of the cosmos. Scientific paradigms shape our understanding of the universe and our place within it. These paradigms act like lenses through which we interpret observations, guiding our theories about the cosmos and its boundaries. When a significant shift occurs, it can alter not just scientific understanding, but also our cultural perceptions and philosophical beliefs. For example, when the heliocentric model emerged, placing the Sun at the center of our solar system rather than the Earth, it transformed the way humanity saw its role in the universe. Suddenly, we were no longer the focal point, but rather a planet among others, orbiting a star in a vast space. This idea propelled the scientific revolution, spurring advancements in navigation, exploration, and our understanding of gravity, all of which expanded the scope of the universe in our collective imagination. As new discoveries arise, such as the expansion of the universe or the existence of dark matter and dark energy, they redefine the boundaries of what we thought was known. Each new insight challenges preconceived notions, prompting society to reconsider questions regarding the universe's size, composition, and even its ultimate fate. The realization that the universe extends far beyond what we can observe hints at a richness that lies beyond our immediate experience, fostering curiosity and inspiring both scientists and laypeople to ponder deeper philosophical questions. These shifts also have practical implications. For instance, advancements in technology that stem from physics and space exploration impact industries, education, and policies. As the boundaries of human knowledge stretch, so does our ability to innovate and tackle contemporary issues like climate change, resource management, and technology-driven challenges. Therefore, the interplay between shifting scientific paradigms and society's understanding of the universe not only informs how we view our cosmic neighborhood, but also affects our actions and priorities here on Earth.